In still other biomes, such as tropical rainforest, temperatures are nearly constant, but rainfall varies seasonally. In the tropics, where seasonal temperature fluctuations are small, annual cycles are dominated by wet and dry seasons. See Figure 4. It is easiest to grasp the similarities and differences among terrestrial biomes by means of a combination of photographs and graphs of temperature, precipitation, and biological activity, supplemented by a few words that describe the species richness and other attributes of those biomes. We use this method in the following pages to describe the major terrestrial biomes of the world. Each biome is represented by a map showing its locations and two photographs that illustrate either the biome at different times of year or representatives of the biome in different places on Earth. One set of graphs plots seasonal patterns of temperature and precipitation at a site in the biome. Other graphs show how active different kinds of organisms are during the year. For high latitude biomes, patterns in the southern hemisphere are 6 months out of phase with those shown, which represent the northern hemisphere. Levels of biological activity, shown by the width of the horizontal bars, change either because resident organisms become more or less active, produce leaves, come out of hibernation, hatch, or reproduce, or because organisms migrate into and out of the biome at different times of the year. A small box describes the growth forms of the plants that dominate the vegetation in the biome and its patterns of species richness. These descriptions are very general and cannot describe the variation that exists within each biome. Tundra is found at high latitudes and in high mountains. The tundra biome is found in the Arctic and high in mountains of all latitudes. Arctic tundra vegetation, which consists of short perennial plants, is underlain by permafrost, soil whose water is permanently frozen. The top few centimeters of soil thaw during the short summers, when the sun shines 24 hours a day. Even though there is little precipitation, lowland Arctic tundra is very wet because water cannot drain down through the permafrost. Plants grow for only a few months each year. Most Arctic tundra animals either migrate into the area only for the summer or are dormant for most of the year. Tropical alpine tundra is not underlain by permafrost, so photosynthesis and most other biological activities continue, albeit slowly, throughout the entire year. More plant growth forms are present in tropical alpine than in Arctic tundra vegetation. Most boreal forests are dominated by evergreen trees. Boreal forest is found equatorward from tundra and at lower elevations on temperate zone mountains. Boreal forest winters are long and very cold. Summers are short, although often warm. The shortness of the summers favors trees with evergreen leaves because these trees are ready to photosynthesize as soon as temperatures warm in spring. The boreal forests of the northern hemisphere are dominated by evergreen coniferous gymnosperms. In the southern hemisphere, the dominant trees are southern beeches, nuthagus, some of which are evergreen. Evergreen forests also grow along the west coast of continents at middle to high latitudes in both hemispheres, where winters are mild but very wet and summers are cool and dry. These forests are home to Earth's tallest trees. Boreal forests have only a few tree species. The dominant animals, e.g., moose, hares, eat leaves. The seeds in the cones of conifers support a fauna of rodents and birds. Deciduous trees, which dominate these forests, lose their leaves during the cold winters and produce leaves that photosynthesize rapidly during the warm, moist summers. Many more tree species live here than in boreal forests. The temperate forests richest in species are in the southern Appalachian Mountains of the United States and in eastern China and Japan, areas that were not covered by glaciers during the Pleistocene. Many genera of plants and animals are shared among the three geographically separate deciduous forest biomes. Temperate deciduous forests change with the seasons. The temperate deciduous forest biome is found in eastern North America, eastern Asia, and Europe. Temperatures in these regions fluctuate dramatically between summer and winter. Precipitation is relatively evenly distributed throughout the year. Temperate grasslands are widespread. The temperate grassland biome is found in many parts of the world, all of which are relatively dry for much of the year. Most grasslands, such as the pampas of Argentina, the belt of South Africa, and the Great Plains of North America, have hot summers and relatively cold winters. Most of this biome has been converted to agriculture. In some grasslands, most of the precipitation falls in winter. California grasslands, in others, the majority falls in summer. Great Plains, Russian steppe. Grassland vegetation is structurally simple, but it is rich in species of perennial grasses, sedges, and forbs. Grasslands are often riots of color when forbs are in bloom. Grassland plants are adapted to grazing and fire. They store much of their energy underground and quickly sprout after they are burned or grazed. Cold deserts are high and dry. The cold desert biome is found in dry regions at middle to high latitudes, especially in the interiors of large continents in the rain shadows of mountain ranges. Seasonal changes in temperature are great. Cold deserts are dominated by a few species of low-growing shrubs. The surface layers of the soil are recharged with moisture in winter, and plant growth is concentrated in spring. Because soils dry rapidly in spring, annual primary production is low. Cold deserts are relatively poor in species of most taxonomic groups, but the plants of this biome tend to produce large numbers of seeds, supporting a rich fauna of seed-eating birds, ants, and rodents. Hot deserts form around 30 degrees latitude. The hot desert biome is found in two belts, centered around 30 degrees north and 30 degrees south latitudes, where air descends, warms, and picks up moisture. Hot deserts receive most of their rainfall in summer, but they also receive winter rains from storms that form over the mid-latitude oceans. The driest large regions, where summer and winter rains rarely penetrate, are in the center of Australia and the middle of the Sahara Desert of Africa. Except in these driest regions, hot deserts have richer and structurally more diverse vegetation than cold deserts. Succulent plants that store large quantities of water in their expandable stems are conspicuous in some hot deserts. Annual plants germinate in abundance and grow when rain falls. Pollination and dispersal of fruits by animals are common. Rodents, termites, and ants are often remarkably abundant, and lizards and snakes typically are rich in species and abundant. The chaparral climate is dry and pleasant. The chaparral biome is found on the west sides of continents at moderate latitudes, around 30°, where cool ocean waters flow offshore. Winters in this biome are cool and wet, summers are warm and dry. Such climates are found in the Mediterranean region of Europe, coastal California, central Chile, extreme southern Africa, and southwestern Australia. The dominant plants of chaparral vegetation are low-growing shrubs and trees with tough, evergreen leaves. The shrubs carry out most of their growth and photosynthesis in early spring, when insects are active and birds breed. Annual plants are abundant and produce copious seeds that fall onto the soil. This biome thus supports large populations of small rodents, most of which store seeds in underground burrows. Chaparral vegetation is naturally adapted to survive periodic fires. Many shrubs of northern hemisphere chaparral produce bird-dispersed fruits that ripen in the late fall, when large numbers of migrant birds arrive from the north. Thorn forests and savannas have similar climates. Thorn forests are found on the equatorial sides of hot deserts. The climate is semi-arid, little or no rain falls during winter, but rainfall may be heavy during summer. Thorn forests contain many plants similar to those found in hot deserts. The dominant plants are spiny shrubs and small trees, many of which drop their leaves during the long dry winter. Members of the genus Acacia are common in thorn forests worldwide. The dry tropical and subtropical regions of Africa, South America, and Australia have extensive areas of savannas, expanses of grasses and grass-like plants with scattered trees. The largest savannas are found in central and eastern Africa, where the biome supports huge numbers of grazing and browsing mammals and many large carnivores that prey on them. The grazers and browsers maintain the savannas. If savanna vegetation is not grazed, browsed, or burned, it typically reverts to dense thorn forest. Tropical deciduous forests occur in hot lowlands. As the length of the rainy season increases toward the equator, tropical deciduous forests replace thorn forests. These forests have taller trees and fewer succulent plants than thorn forests, and they are much richer in plant and animal species. Most of the trees, except for those growing along rivers, lose their leaves during the long, hot, dry season. Many of them flower while they are leafless, and most species are pollinated by animals. During the hot, rainy season, biological activity is intense. The soils of the tropical deciduous biome are some of the best soils in the tropics for agriculture because they are less leached of nutrients than the soils of wetter areas. As a result, most tropical deciduous forests have been cleared for agriculture and cattle grazing. Restoration efforts are underway on several continents. Tropical evergreen forests are species rich. Tropical evergreen forests are found in equatorial regions where total rainfall exceeds 250 centimeters annually and the dry season lasts no longer than 2 or 3 months. They are the richest of all biomes in number of species of both plants and animals, with up to 500 species of trees per km2. Along with their immense species richness, tropical evergreen forests have the highest overall productivity of all ecological communities. However, most mineral nutrients are tied up in the vegetation. The soils usually cannot support agriculture without massive applications of fertilizers. On the slopes of tropical mountains, trees are shorter than lowland tropical trees. Their leaves are smaller, and there are more epiphytes, plants that grow on other plants, deriving their nutrients and moisture from air and water rather than soil. Aquatic biogeography. 3/4 of Earth's surface is covered by water, most of it in the oceans. Earth's oceans form one large, interconnected water mass with only partial barriers to dispersal. Fresh waters, in contrast, are divided into river basins and thousands of relatively isolated lakes. For organisms that cannot survive out of water, terrestrial habitats between bodies of water are barriers to dispersal. However, some aquatic species have flying adults that can disperse widely among water bodies. Others have windborne, desiccation-resistant spores and seeds. Still others are small enough to be transported by mud on the feet of birds. Freshwater environments have little water but many species. Although only about 2.5% of Earth's water is found in ponds, lakes, and streams, about 10% of all aquatic species live in freshwater habitats. Many freshwater taxa that are capable of dispersing across terrestrial barriers are found over several continents. Prominent among freshwater taxa are the more than 25,000 species of insects that have at least one aquatic stage in their life cycle. Typically, eggs and larvae are aquatic, the adults have wings. Some of these insects, such as dragonflies, are powerful flyers, but mayflies and some other species are weak flyers, desiccate rapidly in air, and live no longer than a few days. As you would expect, oceanic islands have few, if any, species of these weak flyers. Similarly, fishes unable to live in salt water can disperse only within the connected rivers and lakes of a river basin. Most families of freshwater fishes that cannot tolerate salt water are restricted to a single continent. Those families with species distributed on both sides of major saltwater barriers are believed to be ancient lineages whose ancestors were distributed widely in Laurage or Gondwana. Water temperature defines marine biogeographic regions. As we saw in Figure 7, ocean water moves in great circular patterns, clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Even organisms with limited swimming abilities can move long distances simply by floating with ocean currents. Nevertheless, most marine organisms have restricted ranges. Why is this true? The oceans may be connected, but water temperatures, salinities, and food supplies all may change spatially. Living successfully in different regions of the ocean requires different physiological tolerances and morphological attributes. Ocean temperatures, for example, can be barriers to dispersal because many marine organisms function well in only a relatively narrow range of temperatures. The main biogeographic divisions of the ocean coincide with regions where the surface water temperatures and salinities change relatively abruptly as a result of horizontal and vertical ocean currents. Figure 9. These temperature changes, in combination with seasonal changes in the amount of daylight, determine the seasons of maximum primary production. Species of marine algae photosynthesize either in summer or in winter, but not during both seasons. Deep ocean waters prevent the dispersal of marine organisms that live only in shallow water. The distance that eggs and larvae of many marine organisms can be carried by ocean currents is determined in large part by the time it takes for larvae to metamorphose into sedentary adults. Relatively few species have eggs and larvae that survive long enough to disperse across wide barriers of deep water. As a result, the richness of shallow water species in the intertidal and subtidal zones of isolated islands in the Pacific Ocean decreases with distance from the larger islands of Indonesia. Figure 10. Regional patterns of species richness. Local species richness is often positively correlated with both productivity and disturbance level. Other patterns of species richness appear at larger spatial scales. As we increase the area we are sampling, the number of species we record increases slowly. Figure 10. However, if our sampling area crosses a biogeographic boundary, the rate at which we add new species suddenly increases. At that point, we have added to our sample another biogeographic region with a different evolutionary history and a different biota. One of the first geographic patterns of species richness observed by biologists was that more species are found in low latitude than in high latitude regions. Species richness on islands and peninsulas is always less than that in equivalent area on the nearest mainland. On islands, species richness is positively correlated with island size, but inversely correlated with distance from the mainland. Figure 11. An influential model relates this pattern to the island's history of immigrations and extinctions. Island biogeography. Species richness is related to rates of immigration and extinction. Over periods of a few hundred years during which speciation is unlikely, the species richness of an area is influenced by the immigration of new species and the extinction of species already present. It is easiest to visualize the effects of these two processes if we consider, as did Robert MacArthur and Edward O. Wilson, an oceanic island that initially has no species. Imagine a newly formed oceanic island that receives colonists from a mainland area. The list of species on the mainland that might possibly colonize the island is called the species pool. The first colonists to arrive on the island are all new species because no species lived there initially. As the number of species on the island increases, a larger fraction of colonizing individuals will be members of species already present. Therefore, even if the same number of species arrive as before, the rate of arrival of new species should decrease until it reaches zero when the island has all the species in the species pool. As we will see, however, the process is unlikely to proceed that far. Now consider extinction rates. At first there will be only a few species on the island, and their populations may grow large. As more species arrive and their populations increase, the resources of the island will be divided among more species. Therefore, the average population size of each species will become smaller as the number of species increases. The smaller population, the more likely it is to become extinct. In addition, the number of species that can possibly become extinct increases as species accumulate on the island. Furthermore, new arrivals on the island may include pathogens and predators that increase the probability of extinction for other species. For all these reasons, the rate of extinction increases as the number of species on the island increases. Because the rate of arrival of new species decreases and the extinction rate increases as the number of species increases, eventually the number of species on the island should reach an equilibrium at which the rates of arrival and extinction are equal. Figure 12a. If there are more species than the equilibrium number, extinctions should exceed arrivals, and species richness should decline. If there are fewer species than the equilibrium number, arrivals should exceed extinctions, and species richness should increase. The equilibrium is dynamic because its beta rate fluctuates, as they generally do. The equilibrium number of species shifts up and down. MacArthur and Wilson's model can also be used to predict how species richness should differ among islands of different sizes and different distances from the mainland. We expect extinction rates to be higher on small islands than on large islands because species populations are, on average, smaller there. Similarly, we expect fewer immigrants to reach islands that are more distant from the mainland. Figure 12b gives hypothetical relative species richnesses for islands of different sizes and distances from the mainland. As you can see, the number of species should be highest for islands that are relatively large and relatively close to the mainland. The MacArthur-Wilson model has been tested. Major disturbances, which serve as natural experiments, sometimes permit colonization and extinction rates to be estimated directly. In August 1883, Krakatau, an island in the Sunda Strait between Sumatra and Java, was devastated by a series of volcanic eruptions that destroyed all life on the island's surface. After the lava cooled, Krakatau was colonized rapidly by plants and animals from Sumatra to the east and Java to the west. By 1933, the island was again covered with a tropical evergreen forest, and 271 species of plants and 27 species of resident land birds were found there. During the 1920s, when a forest canopy was developing, there were high rates of colonization by both birds and plants. Table 1. Birds probably brought the seeds of many plants because, between 1908 and 1934, both the percentage from 20% to 25% and the absolute number from 21 to 54 of plant species with bird dispersed seeds increased. Today the numbers of species of plants and birds are not increasing as fast as they did during the 1920s, but colonizations and extinctions continue, as predicted by the model. Biogeography and human history. The distributions of land masses and species on Earth have had a strong influence on human history. Humans first evolved in Africa, but eventually dispersed throughout the world. In recent times, human cultures from Eurasia came to dominate other cultures. Biogeography gave these cultures a number of advantages. Eurasia happened to have a large number of species of plants and animals that were suitable for domestication. Eurasia was home to 39 species of large-seeded grasses, many more than were found in Africa or the Americas. It also had 72 species of large mammals, compared with 51 in sub-Saharan Africa and 24 in the Americas. 13 of these species, including pigs, horses, cattle, sheep, goats, and camels, were domesticated in Eurasia. None were domesticated in Africa, and only one, the llama, in the Americas. To be amenable to domestication, large mammals had to have three important social characteristics. They had to live in herds, have well-developed male dominance hierarchies, and not defend territories. These traits enabled humans to tame the animals, exert behavioral dominance over them, and keep them in herds. All of the large mammals of Africa lacked one or more of these traits. Besides providing people with food, the domestication of large mammals had other important influences on human history. Many human diseases, such as smallpox and measles, were acquired from domesticated mammals. Eurasian people acquired immunity to these diseases, but people on other continents did not. Thus, when Europeans colonized the New World, they brought with them diseases that devastated the indigenous people. Those unfortunate people transmitted no fatal diseases to the Europeans. In addition, the Europeans had horses, the only domesticated mammals capable of carrying a person at high speeds. Throughout human history, cultures with horses have defeated and dominated cultures without them. In Eurasia, most mountain ranges are oriented in an east-west direction. Therefore, dispersal of people and their domesticated plants and animals was relatively easy, and dispersing individuals were always within climates with similar temperatures and day lengths. Humans dispersed only recently into North America across the high-latitude Bering Land Bridge. They brought with them no domesticated plants or animals, except dogs. North America had few species of grasses with large seeds. Maize, the grass that came to dominate American agriculture, was difficult to domesticate. Its eventual spread northward from its center of domestication in Mexico was possible only after extensive genetic changes that adapted the plants to the very different day lengths and climates of temperate North America. Human history would have been very different if the continents and their biotas had been distributed differently. Thus, the study of biogeography can help us understand ourselves as well as other species. BIOGEOGRAPHICAL zones in India. To a common man, the term wildlife means living things that are neither humans nor domesticated, especially mammals, birds, and fishes hunted by man. An ecologist uses the term biodiversity for the variety of species of all living plants, animals, and microbes living in their natural habitats. India occupies a major part of South and Southeast Asia, the Oriental Realm, one of the 6 biogeographic realms of the world biosphere. Besides this Himalayan region of India falls into the Arctic realm. Geological events in the landmass of India provided conditions for high levels of biodiversity. India's unique geographical position between 3 different centers of evolution, beginning from Gondwanaland, then shifting to northern Eurasia and finally influx from Africa and Ethiopia, led to diversity in its climate, soil, flora, and fauna. India is thus very rich in biodiversity and considered to be one of the 12 centers of origin and diversity of several plant species in the world. India is one of the 12 megabiodiversity countries of the world. The other countries are Mexico, Colombia, Brazil, Peru, Ecuador, Zaire, Madagascar, Indonesia, Malaysia, China, and Australia. India's biological wealth becomes apparent from the fact that it represents 10 biogeographic zones. Table 1, Fig. Point 1. The Indian region is one of the most diverse biogeographic regions of the world, embracing a wide range of topography, from perpetually snow-covered high Himalayan ranges to plains at sea level low-lying swamps and mangroves, island systems, tropical evergreen rainforests, fertile alluvial plains, hot deserts, and high-altitude cold deserts. There are almost rainless areas, as well as the world's highest rainfall areas. The climate ranges from tropical and subtropical and Indo-Gangetic plains and peninsular regions to temperate and Arctic in the Himalayan region. The habitat types vary from the humid tropical western Ghats to the hot deserts of Rajasthan, from cold deserts of Ladakh to the long warm coastline stretches of peninsular India. Thus, a great variety of climatic and altitudinal variations coupled with varied ecological habitats have contributed immensely to the rich vegetational wealth and varied flora and fauna generating very unique biodiversity in India. Wildlife helps in promoting economic activities that brings money through tourism. It contributes towards maintenance of biodiversity. The colorful birds, animals, and other life forms in the forest are important in maintaining the ecobalance. Disappearance of forests or its reduction in area will cause disappearance of wildlife. Table 1. Major biogeographic zones of India, ZSI, 1997. Thus, conservation of forests and wildlife go side by side. Establishment of national parks and wildlife sanctuaries helps conservation of wildlife. Many countries have through legislation banned killing of birds and other animals. In India, restrictions are imposed on killings of lions, tigers, deers, chital, great Indian bustard, and peacocks, etc. Biogeographic zones of India. We have already considered the soil, flora, and fauna of the country earlier in a separate chapter. A brief account of ecological subdivisions of India and their fauna and flora is presented in this section. India is divided into the following 3 ecological subregions. Himalayan mountain system. There are altitudinal as well as east-west variations in this region. There are 3 distinct subzones each with its characteristic fauna and flora. Himalaya foothills. These extend from the eastern frontiers of Kashmir to Assam. Western Himalayas. It includes higher altitudes and Himalayas from Kashmir, including Ladakh to Kumaon. Eastern Himalayas. It includes regions of Sikkim and extends in the east up to NEFA. Peninsular Indian subregion. This is the raised plateau land of the Deccan extending into the floodplains of the Indo-Gangetic basin westwards into the Great Thar Desert of Rajasthan. Tropical evergreen forests or Indo-Himalayan subregion. This is the region of heavy rainfall comprising northeastern India and the western Ghats in south including Malabar coast. Himalayan mountain system. Fauna is typical of both the Oriental and Palearctic regions. Altitude affects the wildlife distribution. Besides altitude, east-west variations also occur due to decrease in monsoon rainfall towards the west. The West Himalayas have low rainfall, heavy snowfall temperate conditions, whereas in East Himalayas, there is heavy rainfall, snowfall only at very high altitudes. At lower altitudes conditions are like tropical rainforests. Flora and fauna of both Himalayas differ. Himalaya foothills. These have characteristic of bar and territe formations and walled ranges in the south. Flora. Natural monsoon evergreen and semi-evergreen forests. Dominant species are sal, silk cotton trees, giant bamboos, tall grassy meadow with savanna haas and terai. Fauna. Big mammals of North India like elephant, sambar, swamp deer, cheetal, hog deer, barking deer, wild boar tiger, panther, wild dogs, hyena, black bear, sloth bear, porcupine, great Indian one-horned rhinoceros, wild buffalo, Gangetic gharial and golden langur. Western Himalayas high altitude region. Flora. Coniferous pine forests, rhododendrons, dwarf hill bamboo and birch forests mixed with alpine pastures. Fauna. Wild ass, wild goat star, markhor, ibex and sheep nyan, Marco Polo sheep, barrel or blue sheep antelopes, teru and two-banded gazelle deers, hondo or Kashmir stag and show or Sikkim stag, musk deer, smaller mammals like marmots and pikes or mouse hares, golden eagle, snow cox, snow partridges, snow leopard, wolf, fox, cats, black and brown bears, birds like Himalayan mono pheasant, western trogopan, coclas, white-crested collie pheasant, griffin vultures, lammer deers, chosen ravens. Eastern Himalayas. Flora. Oaks, magnolias, laurel ls and birches covered with moss and ferns, coniferous forests of pine, fir, yew and junipers with undergrowth of scrubby rhododendrons and dwarf bamboos, lichens, moses, orchids and other epiphytes dominant due to high humidity and high rainfall. Fauna. Red panda, hog badgers, ferret badgers, crestless porcupines, bull antelopes, sero, goral, toucans. Peninsular Indian subregion. It has 2 zones, High Peninsula India and its extension into the drainage basin of the Ganges River system, and Heat Desert region of Rajasthan, the Thar Indian Desert region. Peninsular India. It is home of tropical moist deciduous to tropical dry deciduous and scrub vegetation depending upon the variation in rainfall and humidity. Flora. Sal in north and east extensions, higher rainfall, and teak in southern plateau are dominant trees. West Ghats have evergreen vegetation, flora and fauna similar to evergreen rainforests of northeastern India. In dry areas of Rajasthan desert and Aravalli hills, trees are scattered and thorny scrub species predominate. The forests give way to more open savanna habit. Fauna. Elephant, wild boar, deer, cheetal or axis deer, hog deer, swamp deer, barasingha, sambar, mudjack or barking deer, antelopes, four-horned antelope, nilgai, blackbuck, chinkara gazelle, wild dog or dhole, tiger, leopard, cheetah, lion, wild pig, monkey, striped hyena, jackal, gaur, a bull. Indian desert. Thar desert of Rajasthan has unique flora and fauna. Flora. Thorny trees with reduced leaves, cacti, other succulents are the main plants. Fauna. Animals are mostly burrowing ones. Among mammals, rodents are the largest group. The Indian desert gerbils are mouse-like rodents. Other animals are wild ass, black buck, desert cat, caracal, red fox, reptiles, snakes, lizards and tortoise well represented. Desert lizards include garnets, lacerids and geckos. Among birds the most discussed is great Indian bustard. Tropical rainforest region. Flora. Extensive grassy stands interspersed with densely forested gorges of evergreen vegetation known as sholas occur in the Nilgiris and offshoot of Western Ghats. Sholas also occur in Animalai and Palni hills. The rainforests of the Western Ghats have dense and lofty trees with much species diversity, more than 100 spp. Mosses, ferns, epiphytes, orchids, lianas and vines, herbs, shrubs make diverse habitat. Dipterocarpus spp predominant in these forests. A variety of tropical orchids are found. Stratification in rainforests is very distinct. 3 horizontal layers are distinguished. The lower story has seedlings of palms, cardamom and ginger. Fauna. It is very rich with all kinds of animals. There are wild elephants, gaur and other larger animals. Most species are tree dwellers. The most prominent are hulak given, only 8 found in India, golden langur, calf langur or leaf monkey, Assam macaque and the pigtailed macaque, lion-tailed macaque, nilgiri langur, standard loris, bats, giant squirrel, civets, flying squirrels, nilgiri mongoose, spiny mouse. Andaman and Nicobar Islands. Flora. These are home of tropical rainforests. Giant Dipterocarpus, Terminalia and Lagerstreamia are dominant. There are mangroves also on coastal areas. Fauna. Many species, about 35, of mammals, a number of reptiles and marine animals occur in this area. Among mammals, bats and rats predominate. 3/4 of the total mammals on islands, Andaman pig, crab-eating macaque, homsid and deer, spotted deer, barking deer, hog deer, sambar. Among marine mammals there are dugong, false killer whale, dolphin. Attila on birds, about 250 species and subspecies for rare Narconda bongo, Nicobar pigeon and megapode. There are also other birds like white-bellied sea eagle, white-breasted swiftlet and several fruit pigeons. There are saltwater crocodiles, a number of marine turtles, coconut crab, lizards, the largest being water monitor, 40 species of snakes including cobra, viper, boral and sea snakes and pythons. Mangrove swamps of sunderbans. Sunderbans are delta of the Ganges where both the Brahmaputra and Ganges join and drain into the Bay of Bengal. Flora. The lower tidal zones have pioneer trees like sunraysia and abyssinia. Above this zone, middle level, there are rhizophora, Bruguiera and Ixecaria cereops forests covering nearly 70% of the mangrove forests. Above this level, highland level, there are supporting forests of phoenix, pure or in association with Ixecaria. There are rare area forests in the highest portion with thick undergrowth of phoenix and nipa palms. Fauna. Ash mud skippers are semi-terrestrial gobies, small crabs, land crabs, fiddler crabs, and the dwarf one that has unusual association with sea anemone. Other animals are weaver ants. In the higher regions of mangrove, there are spotted deer, pigs, monitor lizards, monkeys, etc. The most interesting animal is the man-eater sunderbans tige. Floristic botanical regions of India. As Indian subcontinent is characterized with a variety of climate types, flora of the country is a one correspondingly of different types in different parts. For the study of flora, the country has been divided into the following 9 floristic regions. Figure 2 I. Western Himalayas, E. Eastern Himalayas, E. West Indian deserts, I. B. Gangetic plains, B. Assam, B. Central India, B. Malabar, B. the Deccan, and X. Andamans. Western Himalayas. It extends from central region of Kumaon to northwest region of Kashmir. Altitudinally, there are 3 zones of vegetation corresponding to 3 climatic belts. Submontane or lower region, tropical and subtropical. It is represented from about 1,000 to 5,000 feet above sea level in regions of sawalix and adjacent areas. The forest is dominated by timber trees of Shirlea robusta. In riverine regions, trees of Dalbergia sissu are dominant, while in more moist soils, dominant for Cedrela tuna, Ficus glomerida, and Eugenia jambulana. In isolated patches of grasses, there are present trees of Acacia catechu and Butea monosperma. In dry belts towards west, shore robusta is replaced by such xerophytes as Sisyphus, Carissa, Acacia, etc. with thorny succulent euphorbias on slopes. Pinus roxburghii begins to appear at 3,000 to 5,000 feet. Ground vegetation is poor. Temperate or montane zone. It is represented from 5,000 to 11,675 feet. Above sea level, at about 5,500 feet, Pinus longifolia is generally replaced by P. excelsa. From 5,500 feet to 6,000 feet, Cedrus deodara is quite abundant, forming pure forest stands. At these altitudes, Quercus incana also grows as separate patches. In the inner Himalayas and Kashmir, the tulip birch, salix cane, and populus poplar are abundant until the arcane soil types. At higher altitudes, Aesculus indica, horse chestnut, Quercus semicarpifolia, Q. dilatata along with the conifers such as Abies pinbro, Picea morinda, Cupressus florosa, Taxus baupata, etc. are most common components of vegetation. Rhododendron campanulatum grows at higher altitudes. In inner valleys on dry mountains, Pinus ferrariana is also found. In dry areas of Punjab, wheat and barley are cultivated, while in wet valley of Kashmir, rice is a common crop. Other common plants grown in Kashmir are saffron, Crocus sativus, apples, peaches, walnuts, almonds, etc. Alpine zone. It is the limit of tree growth at about 12,000 feet. Known as timber or tree line, where the plant height is considerably reduced. Plants are mostly dwarfed and cushion-shaped shrubs and grasses. At about 15,000 feet, and above snow line, plant growth is almost nil. On lower levels of this zone, some rhododendrons, Betula utilis, and small junipers are present. Above this zone are present many types of herbs, with short period of vegetative growth and flowering. These include primula, potentilla, polygonum, geranium, saxifraga, aster, etc. Eastern Himalayas. It consists of regions of Sikkim and extends in the east up to India in its vegetational zones. It is similar to the Western Himalayas. On the whole, the Eastern Himalayas have more tropical elements, greater variety of oaks and rhododendrons and less of conifers than the Western Himalayas. The chief difference is the higher rainfall and warmer conditions in this part of Himalayas. The tree and snow lines are higher by about 1,000 feet than the corresponding lines on Western Himalayas. Species diversity and vegetation density are higher in the east. This region is also divided into 3 zones. Submontane zone. Due to warm and humid weather, it is typically tropical with dense forests of Shirlea robusta. It extends from the plain foot of the hill up to 6,000 feet. Altitude. In riverine area, there are forests of Dalbergia sissu and Acacia catechu. Mixed forests of deciduous trees like Scirospermum, Cedrela tuna, Bauhinia, Anthocephalus cadamba, Ligustringia parviflora are predominant. Tall trees like Albizia procera, Salmoia, Artocarpus chaplasha, bamboo, Dendrocalamus are important. Temperate zone. It ranges between 6,000 to 12,000 feet. Altitude above sea level. The lower region has several species of oaks, such as Quercus lamellosa and Q. linida, Michelia, Cedrela, and Eugenia. The upper region, which is cooler, has such conifers as juniperus, Cryptomeria, Picea, Abies, and Suga. One bamboo, Arundinaria sp. is also common. Some rhododendrons are also common at higher elevations. Alpine zone. It is above 12,000 feet, where vegetation is devoid of trees. Shrubby growth of junipers and rhododendron is found in grassy areas. West Indian desert, Indian plains. This region consists of parts of Rajasthan, Kutch, Delhi, and part of Gujarat. The climate is characterized by very hot and dry summer and cold winter. Rainfall is less than 70 centimeters. The plants are mostly xerophytic, such as Acacia nilotica, Prosopis spicifera, P. juliflora, Salvador oleoides, S. persica, Tecanella, Capris acula, Tamarix dioica, and Zizicus numeria. The ground vegetation is mostly represented by small Calotropis sp, Panicum antiotail, Eleusine sp, Trigulus terrestris, etc. Some common species used in plantations are Saccharomunda, Panicum antiotail, Cenchrus ciliaris, Capris acula, Tamarix articulata, Prosopis spicifera, P. juliflora, Acacia leucophylla, and Senegal. Gangetic plain. This region comprising Uttar Pradesh, Bihar, and Bengal is most fertile region. The chief climatic factors, the temperature and rainfall together are responsible for distinct type of vegetation. Rainfall is less than 70 centimeters in West UP, being more than 150 centimeters in Bengal. Vegetation is chiefly of tropical moist and dry deciduous forest type. In northwestern DP, near foothills of the Himalayas, Dalbergia sissu and Acacia nilotica are most common. In southwest UP, there are desert areas where characteristic species are Capris acula, Saccharomunda, Acacia nilotica, etc. In eastern BP, Butea monosperma, Doc modica indica, Mahua, terminalia arjuna, argent, buchanania lands, and chironji, Diospyros melanopsilon, tondu, cordia mix of lysera, circulia orens, Boswellia serrata salai, Acacia catechu, care, Azaracta indica, neem, manjifera indica, mango, Ficus bengalensis, Bargad, F. religiosa, Picale are most dominant trees. Besides them, some weeds and grasses like Xanthium spumarium, Cassia tora, Argemone mexicana, Amaranthus sp, Peristriphe bicolliculata, Dicanthemum annulatum, Bothrioploa pertusa, etc. are also present. In Gangetic delta region, extreme swampy and halitic vegetation is common, where dominant species are Rhizophora mucronata, R. conjugata, Acanthus illicifolius, Candelia reedi, Bruguiera generisa, Cereops roxburghiana, etc. Assam. This region receives the heaviest rainfall, with Cherrapunji as much as more than 1,000 centimeters. The temperature and wetness are very high, which responds, ideal for dense tropical evergreen forests. Some of the important trees are Dipterocarpus macrocarpus, Metuiferia, Michelia champaca, Shirlea robusta, Artocarpus chaplasha, Alstinfol scholaris, Circulia alata, Ligustringia flostrigina, Ficus elastica, etc. Some bamboos, as Bambusa pelida, Dendrocalamus hamiltoni, Calamus sp, Grasses Zimperata cylindrica, Saccharum aruminisium, Themeta sp, Phragmites sp, and insectivorous plants like Nepenthes sp. are also present. In northern cooler regions, Alnus nevalensis, Rhododendron arboreum, Betula sp. are also found in hilly tracts. Some conifers like Pinus cassia and P. insularis are also present. Central India. It comprises Madhya Pradesh, parts of Orissa, and Gujarat. Depending upon the amount of rainfall, forests have developed into thorny, mixed deciduous and cell types. The forest vegetation is chiefly constituted by Tectona grandis, Diospyros melanopsilon, Butea monosperma, Terminalphu tomentosa, and Dalbergia latifolia. The thorny vegetation consists of Carissa spinarum, Zizicus rhodinifolia, Acacia leucophylla, Acatechu, Butea, frondosa, etc. Malabar. This region comprises the western coast of India extending from Gujarat in the north to the Cape Cameron in the south. Rainfall is heavy. The vegetation is of 4 types: tropical moist evergreen forests, mixed deciduous forests, subtropical or temperate evergreen forests, and the mangrove forests. The tropical wet evergreen forests are very luxuriant and multi-storied, with such tall trees as Dipterocarpus indicus, Circulia alata, Cedrela tuna, Tectona grandis, and Dalbergia latifolia. Bamboos, like Dendrocalamus strictus and Bambusa arundinacea, are also present. In the Nilgiri hills, there are temperate evergreen forests of such trees as Euria japonica, Michelia nilgirica, and Gordonia obtusa, known as the sholas. The Deccan. This region is drier with rainfall of about 10 centimeters. It includes Andhra Pradesh, Tamil Nadu, and Karnataka. It has a central hilly plateau with forests of Boswellia serrata, Tectona grandis, and Hardwood pinnata, and the eastern dry coromandel coast, with tropical dry evergreen forests of Santalum album, Chandon, Cedrela tuna, and plants like Capris, Philanthus, Euphorbia sp. Andamans. It has a wide range of spreading coastal vegetation like mangroves, beech forests, and in the interior evergreen forests of tall trees. There are some pockets of dry areas also. Important species of the island are Rhizophora, Menusops, Calophyllum, Dipterocarpus, Ligustringia, and Terminalia. Most of the area is now cleared for paddy and sugarcane cultivation. Vegetation of India. This subcontinent has been affected worst by human influences since long line. Due to this, climax formations are very much altered and or destroyed for agriculture and other similar purposes. The present vegetation has suffered immensely from effects of plants, animals, soil, climate, and man. Therefore, the vegetation of the country that we see around us are much interfered. The most important factors used in the classification of vegetation are rainfall, temperature, biotic influences, and life forms. In India, there are 2 most common types of plant formations: high forest and deep grassland. Forest vegetation. Indian forests have generally been classified on the basis of temperature into four major types: I tropical, E montane subtropical, E temperate, and IV alpine. Tropical forests. Common in the warmer plains, ranging from very dense, multi-storied with diverse trees, shrubs and lianas in areas of high rainfall to dry, scrub jungles of thorny bushes and isolated patches in dry areas. Thus, there are two types: moist tropical and dry tropical forests. Moist tropical forests. On the basis of degree of wetness, these are the following three principal types. I tropical wet evergreen forests, where annual rainfall is over 250 centimeters, as in West Coast, Assam, Bengal, and Andaman Islands. They are multi-storied, made up of small trees, shrubs, epiphytes, lianas, and dense brown vegetation. The dominant members are such trees as Dipterocarpus, Hopi, Artocarpus, Mangifera, Emblica, Michelia, Arboretumia, Lagerstroemia, Ixora, and some climbers. Deep tropical moist semi-evergreen forests, better developed in northern and the southern region of country. Trees shed their leaves for brief period. In north, they develop in North Assam and Bengal and parts of Orissa receiving heavy rainfall. There are some evergreen plants also as Artocarpus, Michelia, and Eugenia. The deciduous trees are Terminalia, Terminals, and Churia. Deep tropical moist deciduous forests, in which some trees shed leaves for brief period, some are evergreen and semi-evergreen. They are common in moist areas of Kerala, Karnataka, and South MP and southern parts of North UP, MP, Bihar, Bengal, and Orissa in north. The well-known teak and sal forests belong to this category. In South India, moist deciduous forests are dominated by species of Terminalia, Grewlia, Garrya, Salmolia, Tectona grandis, Adina cordicolia, Melia, Albizia, Delbergia, etc. In the northern half, Sharia robusta is dominant in Gorakhpur and dry regions of UP, Assam, and North Bengal. Other associates of Sal are Terminalia tomentosa, Dillenia sp, Eugenia sp, etc. Dry tropical deciduous forests. Most of their trees remain leafless for several weeks in dry season. In north, such forests are found in the Punjab, UP, Bihar, and Orissa in the regions which are neither wet nor too dry. Trees are of moderate size, 2.5 meters tall, with sparse canopy. Thorny scrubs, grasses, and some bamboos are also present in some regions. In the Punjab and West UP forests, Onophysis latifolia, Acacia catachu, Terminalia tomentosa, Boswellia serrata are dominant with subdominance of Dendrocalamus strictus, Emblica officinale, wood Fordia floribunda, etc. Forests of Sharia robusta are also found scattered in wet areas. In south, such forests are trees with scattered patches of densely grown grasses intermixed with shrubs. Terminalia. Onophysis latifolia, Tectona grandis, Diospyros melanoxylon, Boswellia sp. Fawn the top layer. Followed by smaller plants like Dendrocalamus, Bambusa, Lantana, Helicteris, etc. Common grasses are Panicum, Andropogon, and Heteropogon. Montane subtropical forests. These are found on hills of South India, as Nilgiri, Mahabaleshwar, and Pachmarhi, between an altitude of 3,000 to 5,600 feet. These are cooler than the tropical and warmer than the temperate forests. In southern parts, the common trees are Eugenia, Actinodaphne, Canthium, Mangifera, and Ficus, and climbers are Piper trichostachian, Netum scandens, Smilax macrophylla, etc. The northern areas have rather tailed trees. In eastern Himalayas, due to higher humidities, bamboos, many epiphytes including orchids, and ferns become abundant. Most of the trees are evergreen. The floristic description of eastern and western Himalayas has already been given. Temperate forests. They occur above 5,300 feet altitude, chiefly on mountains of Himalayas and Nilgiri. In Himalayas, oaks and conifers are abundant. Their distribution has already been described. Oaks spawn relatively stable evergreen pure stands. The southern temperate vegetation is chiefly represented by the Cholas near Udicaman, Nilgiri hills in Tamil Nadu. The forests are very dense with extensive growth of grasses and evergreen tall trees, like Bolanocarpus ugilis, Hopi parviflora, Artocarpus hirsuta, Salmonia malvaricum, etc. Their branches are clothed with mosses, many woody climbers, ferns, and other epiphytes. Alpine forests. Sometimes they are subdivided as subalpine forests, alpine scrubs, moist alpine scrubs, and dry alpine scrubs. They are extensive throughout the Himalayas above 11,000 feet. The tree height becomes lesser with increasing altitude, being replaced finally by sparse growth of small plants like sedum, primula, saxifraga, and lichens, etc. The details of the flora are already given in description of the Himalayas. Grassland vegetation. In India, natural grasslands are hardly present, and most of them are maintained in their present to rise stages due to biotic influences. Thus, grasslands are not climax formations but have developed secondarily by the forest destruction. The two major factors that resulted into their secondary development are adaptive and biotic. The grasslands of India are of three major types. I xerophyllus occur in dry regions of northwest India under semi-desert conditions. E mesophyllus calvus savannas are extensive grass. Flats, typical of Wadad st deciduous forests of DP, and E hygrophilus called wet savannas. All these are being controlled under biotic influences. Indian grasslands have been classified by White et al. 1954 into 8 major types which are shown in Table 2. Diverse fauna of India. Like flora, our fauna, animal life is also equally rich and varied. There are about 77,000 known species. These include about 53,000 species of insects, 1,200 birds, 453 reptiles, 372 mammals, 5,000 mollusks, 2,500 fish, and 450 reptiles. Among the mammals we have elephant found in hot wet equatorial dense forests of Assam, Korea, and Karnataka with heavy rainfall. Camel and wild asses are found in hot and arid deserts. Camels are common in Thar Desert. The wild asses are confined to arid areas of the Rann of Kachach. One-homed rhinoceros lives in swampy and marshy lands of Assam and North Bengal. An interesting group, Indian bison, the Indian buffalo, and the nilgai is also found. Chowsing have 4 homed antelope, black buck, Indian antelope, gazelle, and deer are a unique group of Indian animals. The deer species include cashmere stag, swamp deer, spotted deer, musk deer, and mouse deer. Indian lion is most distinct, which is found only in India and African continent in the world. It occurs in thick forests of Saurashtra and Gujarat. Tiger, the most powerful species of the forest, is also found in India. Bengal tiger is found in the sunderbans. Other animals of cat family are leopards, clouded leopards, and snow leopards. The latter are confined to the upper reaches of the Himalayas. Several interesting animals live in the Himalayan ranges. Chief species include wild sheep, mountain goats, ibex, shrew, and tapir. Panda and snow leopard are also found here. There are several species of monkey in India, of which the langur is the most common. Lion-tailed macaque has hair around the face. Bird life in India is both rich and colorful. Tiger is the national animal. Peacock is national bird. Pheasants, geese, ducks, mynas, parakeets, pigeons, cranes, hornbills, and sunbirds are found in forests and wetlands. I1. Applied ecology. Environmental pollution. Global environmental change. Pollution. Pollution is the introduction of contaminants into an environment that causes instability, disorder, harm, or discomfort to the physical systems or living organisms they are in. Pollution can take the form of chemical substances or energy, such as noise, heat, or light energy. Pollutants, the elements of pollution, can be foreign substances or energies, or naturally occurring. When naturally occurring, they are considered contaminants when they exceed natural levels. Pollution is often classed as point source or non-point source pollution. Sometimes the term pollution is extended to include any substance when it occurs at such unnaturally high concentration within a system that it endangers the stability of that system. For example, water is innocuous and essential for life, and yet at very high concentration, it could be considered a pollutant. If a person were to drink an excessive quantity of water, the physical system could be so overburdened that breakdown and even death could result. Another example is the potential of excessive noise to induce imbalance in a person's mental state, resulting in malfunction and psychosis. Growing evidence of local and global pollution and an increasingly informed public over time have given rise to environmentalism and the environmental movement, which generally seek to limit human impact on the environment. Pollution control. Pollution control is a term used in environmental management. It means the control of emissions and effluents into air, water, or soil. Without pollution control, the waste products from consumption, heating, agriculture, mining, manufacturing, transportation, and other human activities, whether they accumulate or disperse, will degrade the environment. In the hierarchy of controls, pollution prevention and waste minimization are more desirable than pollution control. Pollution control devices. Dust collection systems. O cyclones. O electrostatic precipitators. O baghouses. Scrubbers. O baffle spray scrubber. O cyclonic spray scrubber. O ejector venturi scrubber. O mechanically aided scrubber. O spray tower. O wet scrubber. Sewage treatment and wastewater treatment. O API oil water separators. O sedimentation water treatment. O dissolved air flotation. DOF. O activated sludge biocreators. O biofilters. O powdered activated carbon treatment. Vapor recovery systems. Major forms of pollution and major polluted areas. The major forms of pollution are listed below along with the particular pollutants relevant to each of them. Air pollution, the release of chemicals and particulates into the atmosphere. Common gaseous air pollutants include carbon monoxide, sulfur dioxide, chlorofluorocarbons, CFCs, and nitrogen oxides produced by industry and motor vehicles. Photochemical ozone and smog are created as nitrogen oxides and hydrocarbons react to sunlight. Particulate matter, characterized by size PM10 to PM2.5, is produced from natural sources such as volcanoes or as residual oil fly ash from power plants. Diesel particles are another class of airborne particulate matter. Water pollution, by the release of waste products and contaminants into surface runoff into river drainage systems, leaching into groundwater, liquid spills, wastewater discharges, eutrophication and littering. Soil contamination occurs when chemicals are released by spill or underground leakage. Among the most significant soil contaminants are hydrocarbons, heavy metals, MTBE, herbicides, pesticides, and chlorinated hydrocarbons. Radioactive contamination, resulting from 20th century activities in atomic physics, such as nuclear power generation and nuclear weapons research, manufacture, and deployment. See alpha emitters and actinides in the environment. Noise pollution, which encompasses roadway noise, aircraft noise, industrial noise as well as high-intensity sonar. Light pollution includes light trespass, over-illumination, and astronomical interference. Visual pollution, which can refer to the presence of overhead power lines, motorway billboards, scarred landforms, as from strip mining, open storage of trash, or municipal solid waste. Thermal pollution is a temperature change in natural water bodies caused by human influence, such as use of water as coolant in a power plant. The Blacksmith Institute issues annually a list of the world's worst polluted places. In the 2007 issue, the 10 top nominees are located in Azerbaijan, China, India, Peru, Russia, Ukraine, and Zambia. Sources and causes. Motor vehicle emissions are one of the leading causes of air pollution. China, United States, Russia, Mexico, and Japan are the world leaders in air pollution emissions. However, Canada is the number 2 country, ranked per capita. Principal stationary pollution sources include chemical plants, coal-fired power plants, oil refineries, petrochemical plants, nuclear waste disposal activity, incinerators, large livestock farms, dairy cows, pigs, poultry, etc., PVC factories, metals production factories, plastics factories, and other heavy industry. Some of the more common soil contaminants are chlorinated hydrocarbons, CFH, heavy metals such as chromium, cadmium, found in rechargeable batteries, and lead, found in lead paint, aviation fuel and still in some countries, gasoline, MTBE, zinc, arsenic, and benzene. In 2001, a series of press reports culminating in a book called Fateful Harvest unveiled a widespread practice of recycling industrial byproducts into fertilizer, resulting in the contamination of the soil with various metals. Ordinary municipal landfills are the source of many chemical substances entering the soil environment, and often groundwater emanating from the wide variety of refuse accepted, especially substances illegally discarded there, or from pre-1970 landfills that may have been subject to local control in the US or EU. There have also been some unusual releases of polychlorinated benzodioxins, commonly called dioxins for simplicity, such as TCDD. Pollution can also be the consequence of a natural disaster. For example, hurricanes often involve water contamination from sewage, and petrochemical spills from ruptured boats or automobiles. Larger scale environmental damage is not uncommon when coastal oil rigs or refineries are involved. Some sources of pollution, such as nuclear power plants or oil tankers, can produce widespread and potentially hazardous releases when accidents occur. In the case of noise pollution, the dominant source class is the motor vehicle, producing about 90% of all unwanted noise worldwide. Effects. Human health. Adverse air quality can kill many organisms, including humans. Ozone pollution can cause respiratory disease, cardiovascular disease, throat inflammation, chest pain, and congestion. Water pollution causes approximately 14,000 deaths per day, mostly due to contamination of drinking water by untreated sewage in developing countries. Oil spills can cause skin irritations and rashes. Noise pollution induces hearing loss, high blood pressure, stress, and sleep disturbance. Mercury has been linked to developmental deficits in children and neurologic symptoms. Lead and other heavy metals have been shown to cause neurological problems. Chemical and radioactive substances can cause cancer as well as birth defects. Ecosystems. Sulfur dioxide and oxides of nitrogen can cause acid rain, which reduces the pH value of soil. Soil can become infertile and unsuitable for plants. This will affect other organisms in the food web. Smog and haze can reduce the amount of sunlight received by plants to carry out photosynthesis. Invasive species can outcompete native species and reduce biodiversity. Invasive plants can contribute debris and biomolecules allelopathy that can alter soil and chemical compositions of an environment, often reducing native species competitiveness. Biomagnification describes a situation where toxins may pass through trophic levels, becoming exponentially more concentrated in the process. Ocean acidification, the ongoing decrease in the pH of the Earth's oceans. Global warming. Air pollution. Air pollution is a human introduction into the atmosphere of chemicals, particulate matter, or biological materials that cause harm or discomfort to humans or other living organisms, or damages the environment. Air pollution causes deaths and respiratory disease. Air pollution is often identified with major stationary sources, but the greatest source of emissions is mobile sources, mainly automobiles. Gases such as carbon dioxide, which contribute to global warming, have recently gained recognition as pollutants by climate scientists, while they also recognize that carbon dioxide is essential for plant life through photosynthesis. The atmosphere is a complex, dynamic natural gaseous system that is essential to support life on planet Earth. Stratospheric ozone depletion due to air pollution has long been recognized as a threat to human health as well as to the Earth's ecosystems. Pollutants. There are many substances in the air which may impair the health of plants and animals, including humans, or reduce visibility. These arise both from natural processes and human activity. Substances not naturally found in the air or at greater concentrations or in different locations from usual are referred to as pollutants. Pollutants can be classified as either primary or secondary. Usually, primary pollutants are substances directly emitted from a process, such as ash from volcanic eruption, the carbon monoxide gas from a motor vehicle exhaust, or sulfur dioxide released from factories. Secondary pollutants are not emitted directly. Rather, they form in the air when primary pollutants react or interact. An important example of a secondary pollutant is ground level ozone, one of the many secondary pollutants that make up photochemical smog. Note that some pollutants may be both primary and secondary, that is, they are both emitted directly and formed from other primary pollutants. Major primary pollutants produced by human activity include sulfur oxides, SOx, especially sulfur dioxide, are emitted from burning of coal and oil. Nitrogen oxides, NOx, especially nitrogen dioxide, are emitted from high temperature combustion. Can be seen as the brown haze dome above or plume downwind of cities. Carbon monoxide is colorless, odorless, non-irritating but very poisonous gas. It is a product by incomplete combustion of fuels such as natural gas, coal or wood. Vehicular exhaust is a major source of carbon monoxide. Carbon dioxide, CO2, a greenhouse gas emitted from combustion. Volatile organic compounds, VOC, such as hydrocarbon fuel vapors and solvents. Particulate matter, PM, measured as smoke and dust. PM10 is the fraction of suspended particles 10 micrometers in diameter and smaller that will enter the nasal cavity. PM2.5 has a maximum particle size of 2.5 micrometers and will enter the bronchs and lungs. Toxic metals, such as lead, cadmium, and copper. Chlorofluorocarbons, CFCs, harmful to the ozone layer, emitted from products currently banned from use. Ammonia, NH3, emitted from agricultural processes. Odors, such as from garbage, sewage, and industrial processes. Radioactive pollutants produced by nuclear explosions, war explosives, and natural processes such as the radioactive decay of radon. Secondary pollutants include particulate matter formed from gaseous primary pollutants and compounds in photochemical smog, such as nitrogen dioxide. Ground level ozone O3 formed from NOx and box. Peroxyacetyl nitrate can similarly form from NOx and box. Minor air pollutants include a large number of minor hazardous air pollutants. Some of these are regulated in USA under the Clean Air Act and in Europe under the Air Framework Directive. A variety of persistent organic pollutants, which can attach to particulate matter. Sources. Sources of air pollution refer to the various locations, activities, or factors which are responsible for the releasing of pollutants in the atmosphere. These sources can be classified into two major categories, which are anthropogenic sources, human activity, mostly related to burning different kinds of fuel. Stationary sources, as smokestacks of power plants, manufacturing facilities, municipal waste incinerators. Mobile sources, as motor vehicles, aircraft, etc. Marine vessels, such as container ships or cruise ships, and related port air pollution. Burning wood, fireplaces, stoves, furnaces, and incinerators. Oil refining, and industrial activity in general. Chemicals, dust and controlled burn practices in agriculture and forestry management. Fumes from paint, hairspray, varnish, aerosol sprays, and other solvents. Waste deposition in landfills, which generate methane. Military, such as nuclear weapons, toxic gases, germ warfare, and rocketry. Natural sources. Dust from natural sources, usually large areas of land with little or no vegetation. Methane, emitted by the digestion of food by animals, for example cattle. Radon gas from radioactive decay within the Earth's crust. Smoke and carbon monoxide from wildfires. Volcanic activity, which produce sulfur, chlorine, and ash particulates. Water pollution. Water pollution is the contamination of water bodies such as lakes, rivers, oceans, and groundwater caused by human activities, which can be harmful to organisms and plants which live in these water bodies. Although natural phenomena such as volcanoes, algae blooms, storms, and earthquakes also cause major changes in water quality and the ecological status of water, water is typically referred to as polluted when impaired by anthropogenic contaminants and either does not support a human use, like serving as drinking water, or undergoes a marked shift in its ability to support its constituent biotic communities. Water pollution has many causes and characteristics. The primary sources of water pollution are generally grouped into two categories based on their point of origin. Point source pollution refers to contaminants that enter a waterway through a discrete point source. Examples of this category include discharges from a wastewater treatment plant, outfalls from a factory, leaking underground tanks, etc. The second primary category, non-point source pollution, refers to contamination that, as its name suggests, does not originate from a single discrete source. Non-point source pollution is often a cumulative effect of small amounts of contaminants gathered from a large area. Nutrient runoff in stormwater from sheet flow over an agricultural field, or metals and hydrocarbons from an area with high impervious surfaces and vehicular traffic are examples of non-point source pollution. The primary focus of legislation and efforts to curb water pollution for the past several decades was first aimed at point sources. As point sources have been effectively regulated, greater attention has come to be placed on non-point source contributions, especially in rapidly urbanizing, suburbanizing, or developing areas. The specific contaminants leading to pollution in water include a wide spectrum of chemicals, pathogens, and physical or sensory changes. While many of the chemicals and substances that are regulated may be naturally occurring iron, manganese, etc., the concentration is often the key in determining what is a natural component of water and what is a contaminant. Many of the chemical substances are toxic. Pathogens can produce waterborne diseases in either human or animal hosts. Alteration of water's physical chemistry include acidity, electrical conductivity, temperature, and eutrophication. Eutrophication is the fertilization of surface water by nutrients that were previously scarce. Water pollution is a major problem in the global context. It has been suggested that it is the leading worldwide cause of deaths and diseases, and that it accounts for the deaths of more than 14,000 people daily. Contaminants. Contaminants may include organic and inorganic substances. Some organic water pollutants are insecticides and herbicides, a huge range of organoids and other chemicals. Bacteria, often is from sewage or livestock operations. Food processing waste, including pathogens. Tree and brush debris from logging operations. Box volatile organic compounds, such as industrial solvents, from improper storage. DNAPLs, dense non-aqueous phase liquids, such as chlorinated solvents, which may fall at the bottom of reservoirs, since they don't mix well with water and are more dense. Petroleum hydrocarbons including fuels, gasoline, diesel, jet fuels, and fuel oils and lubricants, motor oil, from oil field operations, refineries, pipelines, retail service stations, underground storage tanks, and transport operations. Note, box include gasoline range hydrocarbons. Detergents. Various chemical compounds found in personal hygiene and cosmetic products. Disinfection by products, DBPs, found in chemically disinfected drinking water. Some inorganic water pollutants include spill of oil over the seas is the biggest danger. Heavy metals including acid mine drainage. Acidity caused by industrial discharges, especially sulfur dioxide from power plants. Pre-production industrial raw resin pellets, an industrial pollutant. Chemical waste is industrial byproducts. Fertilizers, in runoff from agriculture including nitrates and phosphates. Silt and surface runoff from construction sites, logging, slash and burn practices or land clearing sites. Macroscopic, that is, large visible items polluting the water are termed marine debris, and can include such items as nurdles, small ubiquitous waterborne plastic pellets, shipwrecks, large derelict ships. Global warming. The term global warming refers to the warming in recent decades and its projected continuation, and implies a human influence. The United Nations Framework Convention on Climate Change (UNFCCC) uses the term climate change for human-caused change and climate variability for other changes. The term climate change recognizes that rising temperatures are not the only effect. The term anthropogenic global warming is sometimes used when focusing on human-induced changes. Causes. Components of the current radiative forcing as estimated by the IPCC Fourth Assessment Report. Main articles: Attribution of recent climate change and scientific opinion on climate change. The Earth's climate changes in response to external forcing, including variations in its orbit around the sun, orbital forcing, changes in solar luminosity, volcanic eruptions, and atmospheric greenhouse gas concentrations. The detailed causes of the recent warming remain an active field of research, but the scientific consensus is that the increase in atmospheric greenhouse gases due to human activity caused most of the warming observed since the start of the industrial era. This attribution is clearest for the most recent 50 years, for which the most detailed data are available. Some other hypotheses departing from the consensus view have been suggested to explain most of the temperature increase. One such hypothesis proposes that warming may be the result of variations in solar activity. None of the effects of forcing are instantaneous. The thermal inertia of the Earth's oceans and slow responses of other indirect effects mean that the Earth's current climate is not in equilibrium with the forcing imposed. Climate commitment studies indicate that even if greenhouse gases were stabilized at 2000 levels, a further warming of about 0.5 degrees Celsius (0.9 degrees Fahrenheit) would still occur. Greenhouse gases in the atmosphere. The greenhouse effect was discovered by Joseph Fourier in 1824 and was first investigated quantitatively by Svante Arrhenius in 1896. It is the process by which absorption and emission of infrared radiation by atmospheric gases warm a planet's lower atmosphere and surface. Recent increases in atmospheric carbon dioxide (CO2). The monthly CO2 measurements display small seasonal oscillations in an overall yearly uptrend. Each year's maximum is reached during the northern hemisphere's late spring and declines during the northern hemisphere growing season as plants remove some CO2 from the atmosphere. Existence of the greenhouse effect as such is not disputed. Naturally occurring greenhouse gases have a mean warming effect of about 33 degrees Celsius (59 degrees Fahrenheit), without which Earth would be uninhabitable. On Earth, the major greenhouse gases are water vapor, which causes about 36 to 70% of the greenhouse effect, not including clouds, carbon dioxide (CO2), which causes 9 to 26%, methane (CH4), which causes 4 to 9%, and ozone, which causes 3 to 7%. The issue is how the strength of the greenhouse effect changes when human activity increases the atmospheric concentrations of some greenhouse gases. Human activity since the Industrial Revolution has increased the concentration of various greenhouse gases, leading to increased radiative forcing from CO2, methane, tropospheric ozone, CFCs, and nitrous oxide. Molecule for molecule, methane is a more effective greenhouse gas than carbon dioxide, but its concentration is much smaller so that its total radiative forcing is only about a fourth of that from carbon dioxide. Some other naturally occurring gases contribute small fractions of the greenhouse effect. One of these, nitrous oxide N2O, is increasing in concentration owing to human activity such as agriculture. The atmospheric concentrations of CO2 and CH4 have increased by 31% and 149% respectively since the beginning of the Industrial Revolution in the mid-1700s. These levels are considerably higher than any time during the last 650,000 years, the period for which reliable data has been extracted from ice cores. From less direct geological evidence, it is believed that CO2 values this high were last attained 20 million years ago. Fossil fuel burning has produced approximately three-quarters of the increase in CO2 from human activity over the past 20 years. Most of the rest is due to land use change, in particular deforestation. The present atmospheric concentration of CO2 is about 385 parts per million ppm by volume. Future CO2 levels are expected to rise due to ongoing burning of fossil fuels and land use change. The rate of rise will depend on uncertain economic, sociological, technological, and natural developments, but may be ultimately limited by the availability of fossil fuels. The IPCC Special Report on Emission Scenarios gives a wide range of future CO2 scenarios, ranging from 541 to 970 ppm by the year 2100. Fossil fuel reserves are sufficient to reach this level and continue emissions past 2100 if coal, tar sands, or methane flat rates are extensively used. Feedbacks. One of the most pronounced feedback effects relates to the evaporation of water. Warming by the addition of long-lived greenhouse gases such as CO2 will cause more water to evaporate into the atmosphere. Since water vapor is a greenhouse gas, the atmosphere warms further. This warming causes more water vapor to evaporate, a positive feedback, and so on until other processes stop the feedback loop. The result is a much larger greenhouse effect than that due to CO2 alone. Although this feedback process causes an increase in the absolute moisture content of the air, the relative humidity stays nearly constant or even decreases slightly because the air is warmer. This feedback effect can only be reversed slowly as CO2 has a long average atmospheric lifetime. Feedback effects due to clouds are an area of ongoing research. Seen from below, clouds emit infrared radiation back to the surface, and so exert a warming effect. Seen from above, clouds reflect sunlight and emit infrared radiation to space, and so exert a cooling effect. Whether the net effect is warming or cooling depends on details such as the type and altitude of the cloud. These details are difficult to represent in climate models, in part because clouds are much smaller than the spacing between points on the computational grids of climate models. Northern Hemisphere ice trends. Southern Hemisphere ice trends. A subtle feedback process relates to changes in the elapsed rate as the atmosphere warms. The atmosphere's temperature decreases with height in the troposphere. Since the emission of infrared radiation varies with the fourth power of temperature, long-wave radiation emitted from the upper atmosphere is less than that emitted from the lower atmosphere. Most of the radiation emitted from the upper atmosphere escapes to space, while most of the radiation emitted from the lower atmosphere is reabsorbed by the surface of the atmosphere. Thus, the strength of the greenhouse effect depends on the atmosphere's rate of temperature decrease with height. If the rate of temperature decrease is greater, the greenhouse effect will be stronger, and if the rate of temperature decrease is smaller, then the greenhouse effect will be weaker. Both theory and climate models indicate that warming will reduce the decrease of temperature with height, producing a negative lapse rate feedback that weakens the greenhouse effect. Measurements of the rate of temperature change with height are very sensitive to small errors in observations, making it difficult to establish whether the models agree with observations. Another important feedback process is ice albedo feedback. When global temperatures increase, ice near the poles melts at an increasing rate. As the ice melts, land or open water takes its place. Both land and open water are on average less reflective than ice, and thus absorb more solar radiation. This causes more warming, which in turn causes more melting, and this cycle continues. Positive feedback due to release of CO2 and CH4 from thawing permafrost, such as the frozen peat bogs in Siberia, is an additional mechanism that could contribute to warming. Similarly, a massive release of CH4 from methane cleft rates in the ocean could cause rapid warming, according to the cleft rate gun hypothesis. The ocean's ability to sequester carbon is expected to decline as it warms. This is because the resulting low nutrient levels of the mesopelagic zone, about 200 to 1000 m depth, limits the growth of diatoms in favor of smaller phytoplankton that are core biological pumps of carbon. Temperature changes. 2 millennia of mean surface temperatures according to different reconstructions, each smoothed on a decadal scale. The unsmoothed annual value for 2004 is also plotted for reference. Global temperatures have increased by 0.75 degrees Celsius, 1.35 degrees Fahrenheit, relative to the period 1860-1900, according to the instrumental temperature record. This measured temperature increase is not significantly affected by the urban heat island effect. Since 1979, land temperatures have increased about twice as fast as ocean temperatures, 0.25 degrees Celsius per decade against 0.13 degrees Celsius per decade. Temperatures in the lower troposphere have increased between 0.12 and 0.22 degrees Celsius, 0.22 and 0.4 degrees Fahrenheit per decade since 1979, according to satellite temperature measurements. Temperature is believed to have been relatively stable over the 1 or 2,000 years before 1850, with possibly regional fluctuations such as the medieval warm period or the Little Ice Age. Sea temperatures increase more slowly than those on land both because of the larger effective heat capacity of the oceans and because the ocean can lose heat by evaporation more readily than the land. The northern hemisphere has more land than the southern hemisphere, so it warms faster. The northern hemisphere also has extensive areas of seasonal snow and sea ice cover subject to the ice albedo feedback. More greenhouse gases are emitted in the northern and southern hemisphere, but this does not contribute to the difference in warming because the major greenhouse gases persist long enough to mix between hemispheres. Based on estimates by NASA's Goddard Institute for Space Studies, 2005 was the warmest year since reliable, widespread instrumental measurements became available in the late 1800s, exceeding the previous record set in 1998 by a few hundredths of a degree. Estimates prepared by the World Meteorological Organization and the Climatic Research Unit concluded that 2005 was the second warmest year, behind 1998. Temperatures in 1998 were unusually warm because the strongest El Niño southern oscillation in the past century occurred during the year. Anthropogenic emissions of other pollutants, notably sulfate aerosols, can exert a cooling effect by increasing the reflection of incoming sunlight. This partially accounts for the cooling seen in the temperature record in the middle of the 20th century, 62, though the cooling may also be due in part to natural variability. James Hansen and colleagues have proposed that the effects of the products of fossil fuel combustion, CO2 and aerosols, have largely offset one another, so that warming in recent decades has been driven mainly by non-CO2 greenhouse gases. Related climatic issues. A variety of issues are often raised in relation to global warming. One is ocean acidification. Increased atmospheric CO2 increases the amount of CO2 dissolved in the oceans. CO2 dissolved in the ocean reacts with water to form carbonic acid, resulting in acidification. Ocean surface pH is estimated to have decreased from 8.25 near the beginning of the industrial era to 8.14 by 2004, and is projected to decrease by further 0.14 to 0.5 units by 2100 as the ocean absorbs more CO2. Since organisms and ecosystems are adapted to a narrow range of pH, this raises extinction concerns, directly driven by increased atmospheric CO2, that could disrupt food webs and impact human societies that depend on marine ecosystem services. Global dimming, the gradual reduction in the amount of global direct radiance at the Earth's surface, may have partially mitigated global warming in the late 20th century. From 1960 to 1990, human-caused aerosols likely precipitated this effect. Scientists have stated with 66–90% confidence that the effects of human-caused aerosols, along with volcanic activity, have offset some of the global warming, and that greenhouse gases would have resulted in more warming than observed if not for these dimming agents. Ozone depletion, the steady decline in the total amount of ozone in Earth's stratosphere, is frequently cited in relation to global warming. Although there are areas of linkage, the relationship between the two is not strong. Figure, recent increases in atmospheric carbon dioxide, CO2. The monthly CO2 measurements display small seasonal oscillations in an overall yearly uptrend. Each year's maximum is reached during the northern hemisphere's late spring, and declines during the northern hemisphere growing season as plants remove some CO2 from the atmosphere. Biodiversity status, monitoring and documentation, major drivers of biodiversity change, biodiversity management approaches. Introduction. The biosphere, the web of life that lives within and depends upon the inorganic spheres, constitutes a vital life support system for man and its existence in a healthy and functional state is essential for the existence of human race. It is a collection of innumerable organisms, the biological diversity, which makes our life pleasant and possible. The term biodiversity was coined by Walter and Rosen in 1985 and is the abbreviated word for biological diversity. Life originated on Earth almost 4 billion years ago, and nature took more than 1 billion years to develop this wide and complex spectrum of life on Earth. Scientists believe that the total number of species on Earth is in between 10 to 80 million. Wilson, 1988. Range. Pollution. Pollution is the introduction of contaminants into an environment that causes instability, disorder, harm, or discomfort to the physical systems or living organisms they are in. Pollution can take the form of chemical substances or energy, such as noise, heat, or light energy. Pollutants, the elements of pollution, can be foreign substances or energies, or naturally occurring. When naturally occurring, they are considered contaminants when they exceed natural levels. Pollution is often classed as point source or non-point source pollution. Sometimes the term pollution is extended to include any substance when it occurs at such unnaturally high concentration within a system that it endangers the stability of that system. For example, water is innocuous and essential for life, and yet at very high concentration, it could be considered a pollutant. If a person were to drink an excessive quantity of water, the physical system could be so overburdened that breakdown and even death could result. Another example is the potential excessive noise to induce imbalance in a person's mental state, resulting in malfunction and psychosis. Growing evidence of local and global pollution and increasingly informed public over time have given rise to environmentalism and the environmental movement, which generally seek to limit human impact on the environment. Pollution control. Pollution control is a term used in environmental management. It means the control of emissions and effluents into air, water, or soil. Without pollution control, the waste products from consumption, heating, agriculture, mining, manufacturing, transportation, and other human activities, whether they accumulate or disperse, will degrade the environment. In the hierarchy of controls, pollution prevention and waste minimization are more desirable than pollution control. Pollution control devices. Dust collection systems. O cyclones. O electrostatic precipitators. O baghouses. Scrubbers. O baffle spray scrubber. O cyclonic spray scrubber. O ejector venturi scrubber. O mechanically aided scrubber. O spray tower. O wet scrubber. Sewage treatment and wastewater treatment. O API oil water separators. O sedimentation water treatment. O dissolved air flotation. O activated sludge biocreators. O biofilters. O powdered activated carbon treatment. Vapor recovery systems. Major forms of pollution and major polluted areas. The major forms of pollution are listed below along with the particular pollutants relevant to each of them. Air pollution, the release of chemicals and particulates into the atmosphere. Common gaseous air pollutants include carbon monoxide, sulfur dioxide, chlorofluorocarbons, CFCs, and nitrogen oxides produced by industry and motor vehicles. Photochemical ozone is smog created as nitrogen oxides and hydrocarbons react to sunlight. Particulate matter, characterized by size PM10 to PM2.5, is produced from natural sources such as volcanoes or as residual oil fly ash from power plants. Diesel particles are another class of airborne particulate matter. Water pollution, by the release of waste products and contaminants into surface runoff into river drainage systems, leaching into groundwater, liquid spills, wastewater discharges, eutrophication, and littering. Soil contamination occurs when chemicals are released by spill or underground leakage. Among the most significant soil contaminants are hydrocarbons, heavy metals, MTBE, herbicides, pesticides, and chlorinated hydrocarbons. Radioactive contamination, resulting from 20th century activities in atomic physics, such as nuclear power generation and nuclear weapons research, manufacture, and deployment. See alpha emitters and actinides in the environment. Noise pollution, which encompasses roadway noise, aircraft noise, industrial noise, as well as high-intensity sonar. Light pollution includes light trespass, over-illumination, and astronomical interference. Visual pollution, which can refer to the presence of overhead power lines, motorway billboards, scarred landforms, as from strip mining, open storage of trash, or municipal solid waste. Thermal pollution is a temperature change in natural water bodies caused by human influence, such as use of water as coolant in a power plant. The Blacksmith Institute issues annually a list of the world's worst polluted places. In the 2007 issue, the 10 top nominees are located in Azerbaijan, China, India, Peru, Russia, Ukraine, and Zambia. Sources and causes. Motor vehicle emissions are one of the leading causes of air pollution. China, United States, Russia, Mexico, and Japan are the world leaders in air pollution emissions. However, Canada is the number 2 country, ranked per capita. Principal stationary pollution sources include chemical plants, coal-fired power plants, oil refineries, petrochemical plants. Principal stationary pollution sources include chemical plants, coal-fired power plants, oil refineries, petrochemical plants, nuclear waste disposal activity, incinerators, large livestock farms, dairy cows, pigs, poultry, etc., PVC factories, metals production factories, plastics factories, and other heavy industry. Some of the more common soil contaminants are chlorinated hydrocarbons, CFH, heavy metals such as chromium, cadmium, found in rechargeable batteries, and lead, found in lead paint, aviation fuel and still in some countries, gasoline, MTBE, zinc, arsenic, and benzene. In 2001, a series of press reports culminating in a book called Fateful Harvest unveiled a widespread practice of recycling industrial byproducts into fertilizer, resulting in the contamination of the soil with various metals. Ordinary municipal landfills are the source of many chemical substances entering the soil environment, and often groundwater emanating from the wide variety of refuse accepted, especially substances illegally discarded there, or from pre-1970 landfills that may have been subject to local control in the US or EU. There have also been some unusual releases of polychlorinated benzodioxins, commonly called dioxins for simplicity, such as TCDD. Pollution can also be the consequence of a natural disaster. For example, hurricanes often involve water contamination from sewage, and petrochemical spills from ruptured boats or automobiles. Larger scale environmental damage is not uncommon when coastal oil rigs or refineries are involved. Some sources of pollution, such as nuclear power plants or oil tankers, can produce widespread and potentially hazardous releases when accidents occur. In the case of noise pollution, the dominant source class is the motor vehicle, producing about 90% of all unwanted noise worldwide. Effects. Human health. Adverse air quality can kill many organisms, including humans. Ozone pollution can cause respiratory disease, cardiovascular disease, throat inflammation, chest pain, and congestion. Water pollution causes approximately 14,000 deaths per day, mostly due to contamination of drinking water by untreated sewage in developing countries. Oil spills can cause skin irritations and rashes. Noise pollution induces hearing loss, high blood pressure, stress, and sleep disturbance. Mercury has been linked to developmental deficits in children and neurologic symptoms. Lead and other heavy metals have been shown to cause neurological problems. Chemical and radioactive substances can cause cancer as well as birth defects. Ecosystems. Sulfur dioxide and oxides of nitrogen can cause acid rain, which reduces the pH value of soil. Soil can become infertile and unsuitable for plants. This will affect other organisms in the food web. Smog and haze can reduce the amount of sunlight received by plants to carry out photosynthesis. Invasive species can outcompete native species and reduce biodiversity. Invasive plants can contribute debris and biomolecules to allelopathy that can alter soil and chemical compositions of an environment, often reducing native species competitiveness. Biomagnification describes a situation where toxins may pass through trophic levels, becoming exponentially more concentrated in the process. Ocean acidification, the ongoing decrease in the pH of the Earth's oceans. Global warming. Air pollution. Air pollution is a human introduction into the atmosphere of chemicals, particulate matter, or biological materials that cause harm or discomfort to humans or other living organisms, or damages the environment. Air pollution causes deaths and respiratory disease. Air pollution is often identified with major stationary sources, but the greatest source of emissions is mobile sources, mainly automobiles. Gases such as carbon dioxide, which contribute to global warming, have recently gained recognition as pollutants by climate scientists, while they also recognize that carbon dioxide is essential for plant life through photosynthesis. The atmosphere is a complex, dynamic natural gaseous system that is essential to support life on planet Earth. Stratospheric ozone depletion due to air pollution has long been recognized as a threat to human health as well as to the Earth's ecosystems. Pollutants. There are many substances in the air which may impair the health of plants and animals, including humans, or reduce visibility. These arise both from natural processes and human activity. Substances not naturally found in the air or at greater concentrations or in different locations from usual are referred to as pollutants. Pollutants can be classified as either primary or secondary. Usually, primary pollutants are substances directly emitted from a process, such as ash from volcanic eruption, the carbon monoxide gas from a motor vehicle exhaust, or sulfur dioxide released from factories. Secondary pollutants are not emitted directly. Rather, they form in the air when primary pollutants react or interact. An important example of a secondary pollutant is ground level ozone, one of the many secondary pollutants that make up photochemical smog. Note that some pollutants may be both primary and secondary. That is, they are both emitted directly and formed from other primary pollutants. Major primary pollutants produced by human activity include sulfur oxides, SOx, especially sulfur dioxide, are emitted from burning of coal and oil. Nitrogen oxides, NOx, especially nitrogen dioxide, are emitted from high temperature combustion. Can be seen as the brown haze dome above or plume downwind of cities. Carbon monoxide is colorless, odorless, non-irritating but very poisonous gas. It is a product by incomplete combustion of fuels such as natural gas, coal, or wood. Vehicular exhaust is a major source of carbon monoxide. Carbon dioxide, CO2, a greenhouse gas emitted from combustion. Volatile organic compounds, VOC, such as hydrocarbon fuel vapors and solvents. Particulate matter, PM, measured as smoke and dust. PM10 is the fraction of suspended particles 10 micrometers in diameter and smaller that will enter the nasal cavity. PM2.5 has a maximum particle size of 2.5 micrometers and will enter the bronchs and lungs. Toxic metals, such as lead, cadmium, and copper. Chlorofluorocarbons, CFCs, harmful to the ozone layer, emitted from products currently banned from use. Ammonia, NH3, emitted from agricultural processes. Odors, such as from garbage, sewage, and industrial processes. Radioactive pollutants produced by nuclear explosions, war explosives, and natural processes such as the radioactive decay of radon. Secondary pollutants include particulate matter formed from gaseous primary pollutants and compounds in photochemical smog, such as nitrogen dioxide. Ground level ozone O3 formed from NOx and box. Peroxyacetyl nitrate can similarly form from NOx and box. Minor air pollutants include a large number of minor hazardous air pollutants. Some of these are regulated in USA under the Clean Air Act and in Europe under the Air Framework Directive. A variety of persistent organic pollutants, which can attach to particulate matter. Sources. Sources of air pollution refer to the various locations, activities, or factors which are responsible for the releasing of pollutants in the atmosphere. These sources can be classified into two major categories, which are anthropogenic sources, human activity, mostly related to burning different kinds of fuel. Stationary sources, as smokestacks of power plants, manufacturing facilities, municipal waste incinerators. Mobile sources, as motor vehicles, aircraft, etc. Marine vessels, such as container ships or cruise ships, and related port air pollution. Burning wood, fireplaces, stoves, furnaces, and incinerators. Oil refining, and industrial activity in general. Chemicals, dust and controlled burn practices in agriculture and forestry management. Fumes from paint, hairspray, varnish, aerosol sprays, and other solvents. Waste deposition in landfills, which generate methane. Military, such as nuclear weapons, toxic gases, germ warfare, and rocketry. Natural sources. Dust from natural sources, usually large areas of land with little or no vegetation. Methane, emitted by the digestion of food by animals, for example cattle. Radon gas from radioactive decay within the Earth's crust. Smoke and carbon monoxide from wildfires. Volcanic activity, which produce sulfur, chlorine, and ash particulates. Water pollution. Water pollution is the contamination of water bodies such as lakes, rivers, oceans, and groundwater caused by human activities, which can be harmful to organisms and plants which live in these water bodies. Although natural phenomena such as volcanoes, algae blooms, storms, and earthquakes also cause major changes in water quality and ecological status of water, water is typically referred to as polluted when impaired by anthropogenic contaminants and either does not support a human use, like serving as drinking water, or undergoes a marked shift in its ability to support its constituent biotic communities. Water pollution has many causes and characteristics. The primary sources of water pollution are generally grouped into two categories based on their point of origin. Point source pollution refers to contaminants that enter a waterway through a discrete point source. Examples of this category include discharges from a wastewater treatment plant, outfalls from a factory, leaking underground tanks, etc. The second primary category, non-point source pollution, refers to contamination that, as its name suggests, does not originate from a single discrete source. Non-point source pollution is often a cumulative effect of small amounts of contaminants gathered from a large area. Nutrient runoff in stormwater from sheet flow over an agricultural field, or metals and hydrocarbons from an area with high impervious surfaces and vehicular traffic are examples of non-point source pollution. The primary focus of legislation and efforts to curb water pollution for the past several decades was first aimed at point sources. As point sources have been effectively regulated, greater attention has come to be placed on non-point source contributions, especially in rapidly urbanizing, suburbanizing, or developing areas. The specific contaminants leading to pollution in water include a wide spectrum of chemicals, pathogens, and physical or sensory changes. While many of the chemicals and substances that are regulated may be naturally occurring iron, manganese, etc., the concentration is often the key in determining what is a natural component of water and what is a contaminant. Many of the chemical substances are toxic. Pathogens can produce waterborne diseases in either human or animal hosts. Alteration of water's physical chemistry include acidity, electrical conductivity, temperature, and eutrophication. Eutrophication is the fertilization of surface water by nutrients that were previously scarce. Water pollution is a major problem in the global context. It has been suggested that it is the leading worldwide cause of deaths and diseases, and that it accounts for the deaths of more than 14,000 people daily. Contaminants. Contaminants may include organic and inorganic substances. Some organic water pollutants are insecticides and herbicides, a huge range of organoids and other chemicals. Bacteria, often is from sewage or livestock operations. Food processing waste, including pathogens. Tree and brush debris from logging operations. Box volatile organic compounds, such as industrial solvents, from improper storage. DNAPLs, dense non-aqueous phase liquids, such as chlorinated solvents, which may fall at the bottom of reservoirs, since they don't mix well with water and are more dense. Petroleum hydrocarbons including fuels, gasoline, diesel, jet fuels, and fuel oils and lubricants, motor oil from oil field operations, refineries, pipelines, retail service stations, underground storage tanks, and transfer operations. Note: box include gasoline range hydrocarbons. Detergents. Various chemical compounds found in personal hygiene and cosmetic products. Disinfection by products, DBPs, found in chemically disinfected drinking water. Some inorganic water pollutants include spill of oil over the seas is the biggest danger. Heavy metals including acid mine drainage. Acidity caused by industrial discharges, especially sulfur dioxide from power plants. Pre-production industrial raw resin pellets, an industrial pollutant. Chemical waste is industrial byproducts. Fertilizers, in runoff from agriculture including nitrates and phosphates. Silt and surface runoff from construction sites, logging, slash and burn practices or land clearing sites. Macroscopic, that is, large visible items polluting the water or termed marine debris, and can include such items as nurdles, small ubiquitous waterborne plastic pellets, shipwrecks, large derelict ships. Global warming. The term global warming refers to the warming in recent decades and its projected continuation, and implies a human influence. The United Nations Framework Convention on Climate Change (UNFCCC) uses the term climate change for human-caused change and climate variability for other changes. The term climate change recognizes that rising temperatures are not the only effect. The term anthropogenic global warming is sometimes used when focusing on human-induced changes. Causes. Components of the current radiative forcing is estimated by the IPCC Fourth Assessment Report. Main articles: Attribution of recent climate change and scientific opinion on climate change. The Earth's climate changes in response to external forcing, including variations in its orbit around the sun, orbital forcing, changes in solar luminosity, volcanic eruptions, and atmospheric greenhouse gas concentrations. The detailed causes of the recent warming remain an active field of research, but the scientific consensus is that the increase in atmospheric greenhouse gases due to human activity caused most of the warming observed since the start of the industrial era. This attribution is clearest for the most recent 50 years, for which the most detailed data are available. Some other hypotheses departing from the consensus view have been suggested to explain most of the temperature increase. One such hypothesis proposes that warming may be the result of variations in solar activity. None of the effects of forcing are instantaneous. The thermal inertia of the Earth's oceans and slow responses of other indirect effects mean that the Earth's current climate is not in equilibrium with the forcing imposed. Climate commitment studies indicate that even if greenhouse gases were stabilized at 2000 levels, a further warming of about 0.5 degrees Celsius (0.9 degrees Fahrenheit) would still occur. Greenhouse gases in the atmosphere. The greenhouse effect was discovered by Joseph Fourier in 1824 and was first investigated quantitatively by Svante Arrhenius in 1896. It is the process by which absorption and emission of infrared radiation by atmospheric gases warm a planet's lower atmosphere and surface. Recent increases in atmospheric carbon dioxide (CO2). The monthly CO2 measurements display small seasonal oscillations in an overall yearly uptrend. Each year's maximum is reached during the northern hemisphere's late spring and declines during the northern hemisphere growing season as plants remove some CO2 from the atmosphere. Existence of the greenhouse effect as such is not disputed. Naturally occurring greenhouse gases have a mean warming effect of about 33 degrees Celsius (59 degrees Fahrenheit), without which Earth would be uninhabitable. On Earth, the major greenhouse gases are water vapor, which causes about 36 to 70% of the greenhouse effect, not including clouds, carbon dioxide (CO2), which causes 9 to 26%, methane (CH4), which causes 4 to 9%, and ozone, which causes 3 to 7%. The issue is how the strength of the greenhouse effect changes when human activity increases the atmospheric concentrations of some greenhouse gases. Human activity since the Industrial Revolution has increased the concentration of various greenhouse gases, leading to increased radiative forcing from CO2, methane, tropospheric ozone, CFCs, and nitrous oxide. Molecule for molecule, methane is a more effective greenhouse gas than carbon dioxide, but its concentration is much smaller so that its total radiative forcing is only about a fourth of that from carbon dioxide. Some other naturally occurring gases contribute small fractions of the greenhouse effect. One of these, nitrous oxide N2O, is increasing in concentration owing to human activities such as agriculture. The atmospheric concentrations of CO2 and CH4 have increased by 31% and 149% respectively since the beginning of the Industrial Revolution in the mid-1700s. These levels are considerably higher than at any time during the last 650,000 years, the period for which reliable data has been extracted from ice cores. From less direct geological evidence, it is believed that CO2 values this high were last attained 20 million years ago. Fossil fuel burning has produced approximately three-quarters of the increase in CO2 from human activity over the past 20 years. Most of the rest is due to land use change, in particular deforestation. The present atmospheric concentration of CO2 is about 385 parts per million ppm by volume. Future CO2 levels are expected to rise due to ongoing burning of fossil fuels and land use change. The rate of rise will depend on uncertain economic, sociological, technological, and natural developments, but may be ultimately limited by the availability of fossil fuels. The IPCC Special Report on Emission Scenarios gives a wide range of future CO2 scenarios, ranging from 541 to 970 ppm by the year 2100. Fossil fuel reserves are sufficient to reach this level and continue emissions past 2100 if coal, tar sands, or methane flat rates are extensively used. Feedbacks. One of the most pronounced feedback effects relates to the evaporation of water. Warming by the addition of long-lived greenhouse gases such as CO2 will cause more water to evaporate into the atmosphere. Since water vapor is a greenhouse gas, the atmosphere warms further. This warming causes more water vapor to evaporate, a positive feedback, and so on until other processes stop the feedback loop. The result is a much larger greenhouse effect than that due to CO2 alone. Although this feedback process causes an increase in the absolute moisture content of the air, the relative humidity stays nearly constant or even decreases slightly because the air is warmer. This feedback effect can only be reversed slowly as CO2 has a long average atmospheric lifetime. Feedback effects due to clouds are an area of ongoing research. Seen from below, clouds emit infrared radiation back to the surface, and so exert a warming effect. Seen from above, clouds reflect sunlight and emit infrared radiation to space, and so exert a cooling effect. Whether the net effect is warming or cooling depends on details such as the type and altitude of the cloud. These details are difficult to represent in climate models, in part because clouds are much smaller than the spacing between points on the computational grids of climate models. Northern Hemisphere ice trends. Southern Hemisphere ice trends. A subtle feedback process relates to changes in elapsed rate as the atmosphere warms. The atmosphere's temperature decreases with height in the troposphere. Since the emission of infrared radiation varies with the fourth power of temperature, long-wave radiation emitted from the upper atmosphere is less than that emitted from the lower atmosphere. Most of the radiation emitted from the upper atmosphere escapes to space, while most of the radiation emitted from the lower atmosphere is reabsorbed by the surface of the atmosphere. Thus, the strength of the greenhouse effect depends on the atmosphere's rate of temperature decrease with height. If the rate of temperature decrease is greater, the greenhouse effect will be stronger, and if the rate of temperature decrease is smaller, then the greenhouse effect will be weaker. Both theory and climate models indicate that warming will reduce the decrease of temperature with height, producing a negative lapse rate feedback that weakens the greenhouse effect. Measurements of the rate of temperature change with height are very sensitive to small errors in observations, making it difficult to establish whether the models agree with observations. Another important feedback process is ice albedo feedback. When global temperatures increase, ice near the poles melts at an increasing rate. As the ice melts, land or open water takes its place. Both land and open water are on average less reflective than ice, and thus absorb more solar radiation. This causes more warming, which in turn causes more melting, and this cycle continues. Positive feedback due to release of CO2 and CH4 from thawed permafrost, such as the frozen peat bogs in Siberia, is an additional mechanism that could contribute to warming. Similarly, a massive release of CH4 from methane flat rates in the ocean could cause rapid warming, according to the flat rate gun hypothesis. The ocean's ability to sequester carbon is expected to decline as it warms. This is because the resulting low nutrient levels of the mesopelagic zone, about 200 to 1000 m depth, limits the growth of diatoms in favor of smaller phytoplankton that are poor biological pumps of carbon. Temperature changes. 2 millennia of mean surface temperatures according to different reconstructions, each smoothed on a decadal scale. The unsmoothed annual value for 2004 is also plotted for reference. Global temperatures have increased by 0.75 degrees Celsius, 1.35 degrees Fahrenheit, relative to the period 1860-1900, according to the instrumental temperature record. This measured temperature increase is not significantly affected by the urban heat island effect. Since 1979, land temperatures have increased about twice as fast as ocean temperatures, 0.25 degrees Celsius per decade against 0.13 degrees Celsius per decade. Temperatures in the lower troposphere have increased between 0.12 and 0.22 degrees Celsius, 0.22 and 0.4 degrees Fahrenheit per decade since 1979, according to satellite temperature measurements. Temperatures believed to have been relatively stable over the 1 or 2,000 years before 1850, with possibly regional fluctuations such as the medieval warm period or the Little Ice Age. Sea temperatures increase more slowly than those on land both because of the larger effective heat capacity of the oceans and because the ocean can lose heat by evaporation more readily than the land. The northern hemisphere has more land than the southern hemisphere, so it warms faster. The northern hemisphere also has extensive areas of seasonal snow and sea ice cover subject to the ice albedo feedback. More greenhouse gases are emitted in the northern and southern hemisphere, but this does not contribute to the difference in warming because the major greenhouse gases persist long enough to mix between hemispheres. Based on estimates by NASA's Goddard Institute for Space Studies, 2005 was the warmest year since reliable, widespread instrumental measurements became available in the late 1800s, exceeding the previous record set in 1998 by a few hundredths of a degree. Estimates prepared by the World Meteorological Organization and the Climatic Research Unit concluded that 2005 was the second warmest year, behind 1998. Temperatures in 1998 were unusually warm because the strongest El Niño southern oscillation in the past century occurred during the year. Anthropogenic emissions of other pollutants, notably sulfate aerosols, can exert a cooling effect by increasing the reflection of incoming sunlight. This partially accounts for the cooling seen in the temperature record in the middle of the 20th century, 62, but the cooling may also be due in part to natural variability. James Hansen and colleagues have proposed that the effects of the products of fossil fuel combustion, CO2 and aerosols, have largely offset one another, so that warming in recent decades has been driven mainly by non-CO2 greenhouse gases. Related climatic issues. A variety of issues are often raised in relation to global warming. One is ocean acidification. Increased atmospheric CO2 increases the amount of CO2 dissolved in the oceans. CO2 dissolved in the ocean reacts with water to form carbonic acid, resulting in acidification. Ocean surface pH is estimated to have decreased from 8.25 near the beginning of the industrial era to 8.14 by 2004, and is projected to decrease by further 0.14 to 0.5 units by 2100 as the ocean absorbs more CO2. Since organisms and ecosystems are adapted to a narrow range of pH, this raises extinction concerns, directly driven by increased atmospheric CO2, that could disrupt food webs and impact human societies that depend on marine ecosystem services. Global dimming, the gradual reduction in the amount of global direct radiance at the Earth's surface, may have partially mitigated global warming in the late 20th century. From 1960 to 1990, human-caused aerosols likely precipitated this effect. Scientists have stated with 66-90% confidence that the effects of human-caused aerosols, along with volcanic activity, have offset some of the global warming, and that greenhouse gases would have resulted in more warming than observed if not for these dimming agents. Ozone depletion, the steady decline in the total amount of ozone in Earth's stratosphere, is frequently cited in relation to global warming. Although there are areas of linkage, the relationship between the two is not strong. Figure, recent increases in atmospheric carbon dioxide, CO2. The monthly CO2 measurements display small seasonal oscillations in an overall yearly uptrend. Each year's maximum is reached during the northern hemisphere's late spring, and declines during the northern hemisphere growing season as plants remove some CO2 from the atmosphere. Biodiversity status, monitoring and documentation, major drivers of biodiversity change, biodiversity management approaches. Introduction. The biosphere, the web of life that lives within and depends upon the inorganic spheres, constitutes a vital life support system for man and its existence in a healthy and functional state is essential for the existence of human race. It is the collection of innumerable organisms, the biological diversity, which makes our life pleasant and possible. The term biodiversity was coined by Walter and Rosen in 1985 and is the abbreviated word for biological diversity. Life originated on Earth almost 4 billion years ago, and nature took more than 1 billion years to develop this wide and complex spectrum of life on Earth. Scientists believe that the total number of species on Earth is in between 10 to 80 million, Wilson 1988, of which 1.4 million species have been enlisted so far. However, we are losing this heritage of millions of years at a very fast rate. The reduction in diversity in life forms is bound to have great consequences for the entire living world. It has become extremely important to study the various life forms on Earth and the causes of their destruction. Biodiversity is the total variety of life on our planet. The total number of races, varieties or species, i.e., the sum total of various types of microbes, plants and animals present in a system is referred to as biodiversity. The word biodiversity is now very widely used not only by the scientific community, but also by the common people, environmental groups, conservationists, industrialists, and economists. So it is very important to have clear idea about the definition of biodiversity, which is recognized as a separate science with its own principles. Some of the important definitions of biodiversity are given here. Biodiversity is the variety of life in all its forms, levels, and combinations. It includes species diversity, genetic diversity, and ecosystem diversity. International Union for Conservation of Nature and Natural Resources, Lucian. The United Nations Earth Summit in Rio de Janeiro defined biodiversity as the variability among living organisms from all sources, including terrestrial, marine, and other aquatic ecosystems and ecological complexes of which they are part. This includes diversity within species, between species, and ecosystems. According to U.S. Congressional Biodiversity Act, biological diversity is the variety and variability among living organisms and ecological complexes in which they occur and encompasses ecosystem diversity, species diversity, and genetic diversity. In the simplest terms, biological diversity is the variety of life in its processes and it includes the variety of living organisms, the genetic differences among them, and the communities and ecosystems in which they occur. In this article, we will present some fundamental aspects of biodiversity and its conservation. Types of biodiversity. Biodiversity is usually studied at three different levels: species diversity, genetic diversity, and ecosystem diversity. Species diversity. Evolution of species diversity has probably been possible because of habitat diversity on Earth. It refers to the variety of species within a region. This diversity could be measured on the basis of number of species in a region. The term biodiversity is commonly used as a synonym of species diversity. It actually refers to species richness in terms of number of species in a site or habitat. Global diversity is typically represented in terms of total number of species of different taxonomic groups. As mentioned before, an estimated 1.4 million species have been identified to date. Species diversity, again, is studied at three levels: alpha diversity, number of species coexisting; at a site, beta diversity, difference in species; complement between patches; and gamma diversity, number of species in a large area, e.g. a country. This series can further be extended to delta diversity for biomes and omega diversity for the entire biosphere. Some authors call it taxon diversity, variety of taxa within a community of an area. It is generally studied at the species level and hence called species diversity. When the taxonomic levels such as genus and family are considered, term taxon diversity is more appropriate. This term is similar to taxa diversity. Genetic diversity. Within a species there are a number of subspecies. Varieties, subspecies, and varieties are recognizable morphological variations within a species. Forms generally used to recognize and describe sporadic variations in a single morphological feature or strains which slightly differ from each other. These differences are due to slight variations in their genetic organization. This diversity in the genetic makeup of a species is referred to as genetic diversity. A species with a large number of varieties or strains is considered to be rich and diverse in its genetic organization. Genetic variations arise in individuals of a species by genic or chromosomal mutations. Genetic variation within populations is considered a prerequisite for adaptation and evolutionary change, and is such an important aspect of biodiversity. Genetic variation is often expressed in terms of alleles, genes occupying the same locus in a chromosome, and is mainly studied at the population level. Genetic variations can be measured by different recent techniques such as allozyme analysis, DNA fingerprinting, polymerase chain reaction, restriction site mapping, and DNA sequencing. Diversities go on increasing at the micro level. Differences in the level of varieties are followed by differences among the subspecies, varieties, and species. Accumulation of these differences at intraspecific level will automatically lead to distinctive character at the species level. Ecosystem diversity. In ecosystem, there may exist different landforms, each of which supports different and specific vegetation. Ecosystem diversity, in contrast to genetic and species diversity, is difficult to measure since the boundaries of the communities which constitute the various sub-ecosystems are not distinct. Ecosystem diversity could best be understood if one studies the communities and various ecological niches within a given ecosystem. Each community is associated with definite complexes. These complexes are related to composition and structure of biodiversity. Loss of ecosystem diversity may be considered as ultimate cause of loss of species and genetic diversity. Community diversity is a synonym of ecosystem diversity and is defined as the diversity of community types within larger areas, ecological units. It should not be confused with habitat variety, which is an expression mainly used for different species of animals which have different habitats. Evolution of biodiversity. Darwin 1859 proposed that species compete and only the fittest survive in nature. It is inferred that under a strong pressure of natural selection, the less fit species are eliminated. From this concept has arisen the competitive exclusion principle, Hard 1960, which is based on the idea that no two species can be exactly equally fit. It states that if two or more species exist in the same habitat, ultimately all but one of them will be excluded. This is the paradox of biodiversity. We expect few species, but we find many in nature. Mechanisms that may be responsible for preventing loss of species by competitive exclusion and allow species diversity to be maintained are as follows. Newman 2000. 1. Each species has an exclusive ecological niche and subjected to conditions where it is fitter than its competitors. 2. A perfect balance is maintained between species loss and gain. The slightly less fit species are eliminated by competitive exclusion, but this process is so slow that there will be time for other species to arise by evolution or to invade from another region. 3. Competition is reduced or prevented because the main controls on abundance or physical disturbance, stresses e.g. low temperature, toxic substances, predation and disease, hence competitive exclusion does not occur. Factors that promote high diversity. Biodiversity varies greatly from site to site over both large and small distances. This variation is due to certain factors that we discuss here. Favorable environmental conditions. It is quite natural to think that species diversity would be greater where the conditions for growth are very favorable for plants and animals. But this is not universally true. Korea 1991 studied the numbers of species of trees, mammals, birds, reptile and amphibians across the USA and Canada in relation to environmental conditions. Species richness of each group showed positive correlation with temperature and solar influx. In relation to these two factors, biodiversity increases with increasing favorableness. The results from the long-term park grass experiment at Rothamsted, England, showed that the more favorable the nutrient regime for plant growth, the lower was the biodiversity. Grind 1973 proposed the highest diversity at intermediate stress or favorableness. Therefore, it can be inferred that there is no universal relationship between species diversity and the prevalence of favorable condition. Heat reducing soil fertility. There is a negative relationship between diversity and soil fertility. Newman 2000. It is necessary to reduce soil fertility to achieve high species diversity in grasslands. The low divertility and high productivity grasslands is because a few species grow tall. There is intense competition for light and low-growing species are eliminated. Heat disturbance. Minor disturbances help to maintain local species diversity. Disturbance of forests by felling of trees. Fires affects the subsequent species composition. Grazing animals in grasslands can be considered disturbance and they can increase diversity. In the past, tropical rainforests have been used for shifting cultivation. The diversity was initiated as a response to such disturbance. The present day forests represent a mosaic of small patches of different stages of succession following disturbance that provides niches and contributes to diversity. Connell 1979. The conclusion is that disturbance can augment biodiversity and diversity managers need to consider carefully what disturbance to allow or introduce. IV heterogeneity of the environment. Environmental heterogeneity increases biodiversity but has no such effect on alpha diversity. Newman 2000. On a landscape scale, patches and mosaics of varying vegetation can be related to differences in exposure, steepness, soil depth, wetness, rock type affecting soil properties and other factors of microclimate and soil. Each species responds differently to the environmental factors and so the proportions of species change. Whitaker 1956 showed that each woody species in the Great Smoky Mountains had a different distribution to altitude and exposure. So if we want to promote beta diversity, we should pay attention to heterogeneity in the physical environment. Bee plant species diversity may promote insect diversity. Company evolution. High plant diversity may promote insect diversity. This is primarily because of coevolution between plants and insects involving secondary chemicals. Harville 1993. The most of the secondary chemicals in plants such as alkaloids, terpenoids and flavonoids are poisonous to most animals. However, there are examples where one insect species being tolerant to one secondary chemical. This gives the insect the ability to eat something that most other insects cannot eat and it may then specialize in eating one plant species. Thus many insects eat only one or a few plant species. Other herbivorous animals tend to show less specificity in their diet. They show preferences between plant species but rarely confine their feeding to one plant species. Thus plant species diversity is likely to promote diversity of insects, but not necessarily of other animals. Global biodiversity. 1.4 million species of various life forms have been enlisted so far. These include 300,000 species of vascular plants, 40,000 species of vertebrates, 800,000 species of insects, 360,000 species of microorganisms. However, these estimates are increasing all the time. A conservative estimate of the total figure would be 14 million. According to some recent estimates, the number of insects alone may be as high as 10 million. This means that only 13% of the total biodiversity on Earth has been described. High total number of species of plants and microbes. Viruses. It is evident from Table 1 that about 4,000 different viruses are known to date. A conservative estimate of the total number of viruses is 400,000. Thus, we know only 1% of the existing viruses. Bacteria. About 5,300 species of bacteria, including 1,700 species of cyanobacteria, have been recorded so far. According to an estimate, total number of bacterial species on the Earth is around 400,000. Fungi and lichens. More than 70,000 species of fungi, including about 17,000 species of lichens, are known to us. The conservative figure for existing fungal species on the Earth is about 1.5 million. Algae. So far 40,000 species have been described and another 300,000 species are believed to exist on the Earth. Algae yet to be described are likely to come from open ocean as well as from polar regions. Bryophytes. So far 19,000 species of bryophytes are known, of which about 10,000 species are mosses, 8,000 species liverworts and 800 species of hornworts. The number of bryophyte species is likely to increase to about 30,000 if more areas are explored. Pteridophytes. The pteridophytes are vascular land plants and together with gymnosperms and angiosperms dominate terrestrial communities of the world. There are about 15,000 species of pteridophytes known to us. Gymnosperms. Most species of gymnosperms are trees, although a few species are shrubs. There are about 750 species of this group. Angiosperms. The angiosperms of flowering plants constitute the most diverse group of vascular plants. There are about 300,000 species described so far. This group is very recent, 35 million years to evolve in the geological history, but have become the most dominant of all plants because of their great evolutionary capabilities. Plant families vary considerably in the number of their constituent species, e.g. the Orchidaceae contains 25,000 35,000 species and the Leguminosae about 15,000 species. A total of 31 families comprise 62% of the known angiosperm species. 36 families like Ledoxaceae are monospecific. The total number of species of animals. Invertebrates as a whole includes little over 1 million species, distributed among 9 major phyla. These include 800,000 species of insects, 5,000 species of sponges, 38,000 species of mollusks, and 9,000 species of crustaceans. Table 1. The number of species of vertebrates in the world is about 40,000. These include 2,400 species of amphibians, 6,100 species of fish, 6,300 species of reptiles, 9,035 species of birds, and 4,230 species of mammals. Table 1. Detailed distribution of species spread worldwide. Eat the megadiversity countries of the world. Warm and humid regions in between the tropics of Cancer and Capricorn are provided with a rich and diverse plant, animal, and microbial life. In this wide belt around the globe occur more than half of the total number of species present on our planet. Countries which happen to lie in this zone are referred to as megadiversity countries, as they possess a wide variety of plants and animal species. These countries are Brazil, Colombia, Mexico, Indonesia, Peru, Malaysia, Ecuador, India, China, Zaire, Madagascar, and Australia. Table 2 provides the approximate number of flowering plant species recorded in the megadiversity countries on the Earth. Table 2. The megadiversity countries and the number of flowering plant species. S number, country number, of flowering plant species. 1 Brazil 55,000, 2 Colombia 45,000, 3 China 30,000, 4 Mexico minus 25,000. 1 Brazil 55,000, 2 Colombia 45,000, 3 China 30,000, 4 Mexico minus 25,000, 5 Australia 22,506, Indonesia 20,007, Peru 20,008, India 17,500, 9 Malaysia 15,010, Ecuador 15,011, Zaire 10,012, Madagascar 10,000. IV endemism and hotspots of biological diversity. Endemic species can be defined as those species which are confined only to a particular locality. There are two important categories of endemic species: paleoendemics and neoendemics. Paleoendemics are phylogenetic allied distinct taxa which arose in tertiary and bound islands or environmentally isolated situations. Neoendemics are those which have arisen relatively recently. Endemism represents a unique step in the process of evolution which could be perpetuated and sustained only in the locality concerned depending on the environmental quality. It is the environment which is instrumental in the operation of the process of natural selection. This makes the habitats in which endemic species thrive very important. The importance of the habitat is further highlighted by the fact that in most of the cases such localities possess a number of endemic species distributed in several taxonomic categories. In the process of natural selection, changes which confer some disadvantage to the organisms to survive in the existing environmental condition are eliminated while those changes which are advantageous are retained. There should always be a sustained effort to conserve the endemic species in their habitat. Areas where high levels of species richness, threat and endemism coincide are termed as hotspots. Myers 1988 first identified 10 tropical forest hotspots characterized both by high level of plant endemism and by serious level of habitat loss. In 1990, Myers added further 8 hotspots, including 4 Mediterranean type ecosystems. In 1996, Conservation International (CITES) decided to undertake a reassessment of the hotspots concept, including an examination of whether some key areas had been overlooked. 3 years later, 1999 N. Extensive global review was undertaken for the designation of biodiversity hotspots, and 25 biodiversity hotspots were identified. Myers et al. 2000. To be identified as a hotspot, a region must meet 2 strict criteria. It must contain at least 1,500 species of vascular plants greater than 0.5% of the world's total as endemics, and it has to have lost at least 70% of its original habitat. These areas 25 hotspots contain 44% of the world's plants as endemics and 35% of the terrestrial land vertebrates in an area of 1.4% of Earth's land surface. Recently, 34 biodiversity hotspots have been identified covering only 2.3% of the Earth's land surface. Over 50% of the world's plant species and 42% of all terrestrial vertebrate species are endemic to these 34 designated hotspots. The 34 hotspots, distributed in different regions of the world, are listed below. North and Central America. 1. California floristic province. 2. Caribbean islands. 3. Madrian pine oak woodlands. 4. Mesoamerica. South America. 5. Atlantic forest. 6. Cerrado. 7.